of column, you can see the yellow square, which is only 12.6%. Rest is all gray energy. Okay? That means we are still dependent on, majorly on, 88% of our energy usage is not renewable. Okay? It's all gray energy. It's emitting CO2 or many other hazardous gases. The good thing is the electricity generation, almost 30% of electricity generation is now renewable based. And this is all due to photovoltaic and wind, the way it has progressed in the past. So that's something which you can clearly see within a decade from 21%, the electricity generation has gone to 30%, almost like 1/3 of the total of energy produced in the world now. Investments are going on fine, almost 30% with renewable energy you can see, but is that enough? Perhaps not. We need almost 3 times more of that. That means what we require is almost $1 trillion a year of budget to actually meet our demand. So this is where, if you look energy consumption by year, you can see who is consuming very more. Almost 49% of our energy is going in controlling our space, right? Like space heating, space cooling. That's the total energy consumption taking, So it's a very huge chunk going there. Then comes fuel. Almost like 28.6% comes by fuel, and electricity comes 22.7%. So that's the total sector division in 3 parts that I have made, in a major way. But if you look at how much generation of renewable has taken place per year, last year it was, and I think in 2021 it was 314.5 gigawatt, and in 22 it became 348 gigawatt. Now, those who may not understand how much a gigawatt is like, so let me give you a picture. In UK, the total capacity that UK uses is about 70 gigawatt, slightly over 70. So every year we are producing 3 times the UK's capacity, even more than that. So which is a very remarkable way that, how that, renewable energy progressing. But that's not sufficient as to meet the climate change action plans, right? That's why we have to almost triple the manufacturing. That's a major challenge. Here is something, the snippets I've taken from International Energy Agency, which gives an estimation how from 2020 to 30 to 2050, how different kind of technologies are going to take share and how much we require basically from solar and wind to take lead on that part, because capacity addition, if it has to happen, we have to multiply by 4 times to the capacity now we are having right now. Okay? That's the only way we can meet the demand. And so, this is again telling you the money is required. You can see the graph at the bottom is telling that's almost in the range of by 2050, we will have to have allocation of about $10 trillion. To meet that, do we have that money? So we have to keep asking that. India's target about 5 trillion economy, right? But we're talking twice of that money to go, right? This is a huge challenge. So all the bigger nations in the world have to come together to actually face this challenge and deal with this challenge. And in that only way, we can actually bring down the carbon dioxide emission, but this is one gas only we're talking, right? Methane is another going to be a major contributor in the future. So, as I say, even if this we can curb, would be a big success. I'm just giving you a kind of idea about for those young minds who are willing to get into PhD or want to do something. This is a Scopus data that I've taken from Elsevier. And by the way, I'm associate editor of Solar Energy Journal also. So I get to know all these data sometimes. But you see in this, by year 2000, millennium year, the penetration of renewable energy and clean energy technologies or towards net zero technologies were only 1% and below. Now we are talking more than 5%, right? So almost five-fold of increase has taken place. Almost like 14 million publications have gone in the last few years. So it tells definitely there is a very good kind of trend going on. People are coming more and more, doing more research. You know, if you pump more energy and research into it, you get more solutions, right? So this is how it's all like, and we know from our experience, we have to put time, effort, and money to get to the solution. If I talk about quickly about UK's perspective about climate change, Royal Society has come up with their kind of documentation. It was a year ago. There were 12 indicators they talked about, critical areas of climate action plan. And this talks about all those important plans that one must have to curb the climate change action. Okay, so this is something, because our consortium, we've been doing a kind of collaboration with India, pretty much in a consortium. We thought we have taken out some of the things like water, energy, and food as a nexus challenge, what we call as, to actually take for a climate action. So funneling out from here, this is what we have taken. I'm going to show you in the next slide how we're doing it. So if you look into the Royal Society document, it talks about climate science adaptation and resilience. That's one strand. Then energy transitions could be another, and land, food, and health. This is third strand, and transforming economic systems, which covers, you can see the technology and the processings, hydrogen, next generation batteries, low carbon heating and cooling, all the carbon capture and storage, all these become kind of energy transition technology that one has to adopt. So this is the kind of future technologies, or you can call it like new energy vectors we may have to adapt. So with this kind of ideas, in the past I had my legacy APEX program that you see almost the funders gave us almost in the range of £8 million to actually continue that. And we had about 6-7 partners in India, 5 were from the UK side. I was lead of that program, APEX. And then that's what brought me back here to India and got connected with a lot of institutions in India here. IIT Delhi, IIT Bombay, for instance, ISC Bangalore, CSR Bangalore. Some of the CSR institutions were also our partner, like IICT Hyderabad, NPL, and NCL. They were also our partners. And we had Oxford, Cambridge. I was in Loughborough University, and then Brunel. I went ahead further from there. But these were some of the UK institutions were collaborating one-to-one with these institutions, and that was quite a success. Based on that success, we had another program called Sunrise, which was GCRF money Grand Challenge Research Fund. So we had about 7 million to continue our research on bringing capacity change, capacity strengthening, plus looking into new generation technology in solar. That was our aim. So something that we successfully carried out. And then based on that, the funding body had asked us last year to actually map out the themes of net zero. So for that, I took a lead on how to actually define those areas of activities we can take in future. And that's what I'm saying is, on the left side, bottom corner, you can see food, water, energy nexus is one that we are after at the moment. And so we are having a consortium we are trying to form and to bid for some kind of current calls which are there in the UK called Ayrton Fund, and one Indo-UK call which is likely to come sometime soon. So that's what we are targeting. And this is the challenge theme that we have taken, water, energy, food nexus, right? I'm not going to dwell too much in here because I have to really do justice to my other part of activities that I must share with you. How much time do I have? Chair?
Yeah, we have 5 minutes.
5 minutes only? Oh dear.
No, 10 minutes. Sorry.
Okay,
So,
well, thank you, great. Okay, so second part of my activity is going to tell you about what actually I do in materials device research, right? So something that can clearly define my portfolio of activities. So thin film depositions that I have done intensively in my life, vacuum and non-vacuum depositions, and you can see the range of techniques like sputtering, MB evaporation, molecular beam epitaxy. Plus, I also have spray, electrostatic spray deposition, Doppler braiding, screen printing, spray pyrolysis. Electrodeposition is something which I started my career with in 1984. So I was depositing gallium arsenide and cadmium telluride and so many other kind of semiconductors using that. So you can see the range of applications which I have already carried out on those, which are listed there. You can have a look at them. I'm not going to dwell too much on that. I'll tell you straight away now that something which I have done on CIGS, which is copper indium gallium selenide, and cat telluride, I had about 800,000 pounds from one actually industry-led program called TSB, Technology Strategy Board, where we developed this machine. This is a pilot line for CIGS. We can build 30 by 30 centimeter A4 size of cells. And these are, this machine is installed, but it requires a lot of money. So because no funding body is going to give any money to this, we are going to make a startup to have venture capitalist funds available to take it through. So this is something planned going on. The second technology was cadmium telluride, and I had a fund about 1.6 million in 2008 with partners like Pilkington, which are float glass manufacturers. They're the largest manufacturer of the glass. I mean, 70% market they capture, and Arup, who are the built environment specialists. So I went on to prepare thin kind of transparent photovoltaic windows, right? That was our project, which was highly successful. And then I went on to do some new generation solar cells approach also while I was at Imperial College working on this new technology built from Michael Gressel in 1991. And I went on to actually master this technology for flexible solar cells, which I did. And very easy way to make it, like you start with glass, make some TiO2 film, which is kind of very compact film. Then you have porous titania film, which can be sensitized with kind of either sensitizer like ruthenium dyes or quantum dots. And from the other side, you can bring counter electrode with platinum on glass, strap it, fill with the electrolyte, and here is the cell. You can build this cell in 2 hours, no problem in the lab. But it degrades very fast as well. And so the good sealing has to happen, or some new kind of technologies, or maybe the elements that have to be figured out. So there's a lot of scope for the material research here as well. And it's got stuck somehow at this stage. But the offshoot of this activity for me was rewarding, because in APEX program, we went on to discover actually perovskites. The perovskite solar cell, Henry Snaith was my partner from Oxford University, who actually discovered this technology. You can see in the second block, initially 11%, and then within now 10, 12 years time, now we're talking close to 26% cells. This material is in abundance. So if stability of this technology can be really sorted, this can go everywhere. Based on this, we won actually the first Newton Prize in 2017. So this APEX program, actually we were actually chosen out of 250 projects all over the world. Then comes, well, stability kind of work with IICT Hyderabad we did, and this was quite a remarkable work that we were able to actually make hydrophobic coating on the whole conductor, which was able to actually arrest the water degradation onto the cell. For almost like dipping in the cell into 2 hours was still were quite intact. But as I say, the efficiency numbers dropped significantly, so a lot of scope of research still goes on here. Another activity that I did during my, in fact, I want to mention here specific for young mass, here, specific because this is the work I did during my PhD. And at that time, I was worried what was happening, because I was making a Schottky diode, and it started behaving like a switching kind of, thyristor. I said, what is this? I was preparing something, has become something else. So I was confused, but my confusion led me to discover this memristor material, right? This device was the first device that I realized with my own hands in May 1988. Professor Chua from California had predicted this as a fourth circuital element, yeah, called memristor in 1971. And so we based on that, something that I can say I cherish this my work. So once you're getting a negative result, don't feel that it is a wrong result. Try it, and try to feel and find out why the phenomenon is happening. So I can quickly show you. Later on, HP actually got it patented, this technology, and they published the same data in Nature. Okay, you can see on left is my graph that I published in Journal of Semiconductor Science and Technology, a low impact factor journal, and this is something, same kind of strategy. We challenged them, and we are now getting good answers from them. Anyway, innovation and lighting is something that we have also done. My postdoc, Dr. Ali Salamia, who's now become a senior lecturer at South Bank, he had developed laser-induced lighting. And this lighting was almost like we could achieve 4,000 lumens of intensity with only 14 watts of laser light, or laser diode, sorry. And you can see this is a kind of intense, almost like 4 suns of intensity we were getting here. It was almost like a headlight lamp. We were actually going to go with Jaguar Land Rover at some stage. Then we also have developed AC electroluminescent lighting modules, which we think is a cold emitter. And so we can have some activities they were planning with Pilkington Glass Company on what we call as vertical farming approach. Then another innovation that we have done is on air quality. This is something that I have patent on, or diesel particle filters. Again, 2 of my researchers, postdocs, were involved in that activity. A DPF is something you can see. The conventional DPF is a honeycomb structure, which gets fitted into a kind of tail end of the pipe of exhaust. But if you're not running your vehicle at a high speed, it can get, the particles can actually get mixed up, and it can fill the pores and holes and can get jammed up. And only thing you can do is to just throw it off. And this is not a kind of cheap material. It's almost like 2,000 pound worth of a piece of technology, and you can't afford to actually change every fortnight. So something has to be done. So we went down to actually my postdoc was having a Jaguar car that he has just gifted to his wife, and it got jammed into a few weeks. And the guys, when he went to the garage, they said, like, you have to run this vehicle at 70 miles an hour to get the exhaust temperature high, to burn all the carbon. So we went out to have discovered. So what I'm saying is, with limited time that I cannot go into much description, but what I can tell you that at high RPM with high load, we are getting only particles which is meeting the Euro 6 regulations. And so this is a technology that we are also talking to Ashok Leyland and Tata Motors, who can embrace this later on. Last thing that I want to talk about is digitization of sputter deposition, because I have been working intensely on solar cell activities. Transparent conducting oxides are a very important element for any electro, what should I say, like if you're using any like solar cells or LED lamps, you have to, or any flat panel devices, TCOs are the material choice. So something that we are working here on, and we thought, why not we monitor and look into how the, in situ, how can we monitor the plasma itself, which actually governs the quality of TCO that's going to end up. So what we did, we started using the color characteristic of plasma itself, and in terms of color indexes, we were able to actually monitor those. So instead of looking at the spectral changes that you cannot monitor in situ very easily, but you can monitor the color very easily. So we got a handle, we published a paper, a couple of papers on this, and we can see that, we can point out the stability of the plasma pretty much here initial phase of instability were recorded. There is going back and forth here. Now, once it stabilizes, we can know, okay, it's, the stability of plasma will lead to stable kind of material that we want to actually produce. So we also have carried out some artificial intelligence technique for sputter deposition of TCOs. And these are the two methods, like I'm sure some of you might know, artificial neural network, ANN, and CNN, which is convolutional neural network, are the two major techniques that my postdoc actually got this actually. He got into this sort of area to explore more because we had a lot of data during the pandemic time, and we thought, why not to actually make use of that? And so what we found out that actually we did the modeling, and we could see that the coefficient of determination, which is R square, comes very close to almost unity in some of the cases. So we were able to actually look into the different approaches and R square values in terms of how they behave, like some were moderate, some were good. So we were able to actually find out the relevance of artificial intelligence even to the processing techniques of the material that we can actually make. So here my conclusions are that net zero emission requirements are real and necessary, and they are now necessity and no more just a statement. Ramping up the existing energy generation storage technology will be required 4 times in the next 5 years to meet the net zero requirements, and they may lead to global emission supply issues. And, well, low upfront processing cost of solar cell manufacturing, which involves low capex, such as organic solar cell, dye-sensitized, perovskites, can be ideal for developing countries, but with a caveat, as I said, the stability has to go 20 years of lifespan. Unless that happens, it is not going to be into production line. So R&D efforts in nanomaterial and nanotechnology will still play a major role. So the future is yours. All youngsters must actually pay attention here. Materials technology or nanotechnology and nanomaterials are going to be still very there, And with that, I would say our focus is going to be water, energy, food nexus in this manner to actually achieve net zero transition or targets that we have for 2050 in UK. I think in India it is about 260, but we'll try to achieve much earlier. Okay, so with that I end my talk. Thank you.
Thank you. Almost finishing in time allotted to you.
Some of my collaborators here, just thought to mention here, some industries and some of the workers that I have especially mentioned to my PhD student, Salim, Ali Salimia, and some other people who actually are not named here. Sorry about that. Thank you.
Any quick question? One question. Yes, Professor.
Please.
Nice to see you after almost 10 years. I'm Dr. S. Diwali.
Aha.
We were associated in RISE program, RISE.
Oh, yes.
I was in CSR and
Oh, right. Good to see you.
So I just wanted to know, people are focusing about this perovskites for solar cells, non-lead based perovskites.
Correct.
So what is the efficiency as of now?
Yes, I think lead is one of the problems. Although the claims made by Oxford PV is that they are using very small amount, but when you go to large manufacturing volumes, perhaps that may become significant. And leach test has proven that, well, lead comes out very easily out. So that's an issue. But once we try to replace, say, lead by, say, tin, which I'm also working on that, we are finding that the efficiency level drops significantly low. We are getting anywhere around 7 to 8%, sometime 8%. That's also with difficulty. Yeah. So a lot of changes actually. Once the configuration of you push another atom into, large kind of, it's just a large molecule, believe me. So it changes the kind of configuration of the whole atoms, and it is still an open challenge and open question as to why this is all happening. Okay? So a lot of scope here is maybe artificial intelligence can help us in finding out what material choice we may have to have. But this is a challenge still.
Yeah, because lead is moving. I think lead will not be allowed to move.
Lead will continue, definitely.
Secondly, stability.
Stability is a challenge, exactly. Yeah, yeah.
So that is another issue.
See, stability won't be a challenge if we are ready to pay good amount of money for, say, sealing. Okay? But then it defeats all the purpose. Yeah? The cost becomes almost 3 times higher.
So we have been seeing this for flexible solar cells, the efficiency. The moment you scale up, the efficiency
Drops.
goes down.
That's
So
right.
what are the efficiency for large scale production of flexible solar cells?
For flexible, are you talking in terms of organic?
Organic VSSC,
I think you can have small area, 18% have been given, but anywhere around 11 to 12, I won't bet more than that, because spreading resistance losses, etc., and, lot of processing kind of challenges which they are there, they sort of get away from, they don't do all the process because to manage the processing and manufacturing line working, some compromises have to be made. So the efficiency numbers go drastically down. I don't think anywhere around, even if it's 12%, I'll be very pleased. Thank you.
Okay, for Professor Upadhyay for excellent talk. In fact, he began with the challenges of energy and energy future, how to meet that, So the whole focus was on that, and then very briefly talked about thin film is also an area to be concerned. So we thank the professor for his wonderful talk with the usual acclamations, Thank you very much. Yeah. The next talk is by Professor Rajaram Bal, who is the senior principal scientist at the CSR India IIP Dehradun, and he's the one who got a PhD from another CSR prestigious laboratory, NCL Pune, and his interest of research includes synthesis of supported metal catalysts, mixed metal oxides, nanomaterials, nanoporous materials, zeolites, and hydroxyl calcides, characterization and applications of above catalytic systems in selective oxidations of hydrocarbons, ammono oxidations, low temperature water gas reactions, preferential oxidations, reactions for fuel cell applications, methane activation, glycerol to value-added products, CO2 fuel, upgradation of biofuels, and he has many credentials with him, including Humboldt Fellowship we had in 2002 to 3, JSPA Postdoctoral Fellow 2004-6, DST Young Scientist Fast Track, there's an award, and over 200 publications and over 5,000 citations. So I present to you this wonderful speaker again, Professor Rajaram Bal, and give your talk, and your time given to is 25 minutes. Shorter will be preferred. Thank you.
Thank you, Chairman, for the introduction. Good afternoon, everybody. First of all, I would like to thank the organizers for inviting me. Today, I will talk mainly on methane activation over nanostructure catalyst. Now, methane, this is the simplest molecule, but it is the most stable molecule. And there are plenty of methane available in the earth, and you can see the data here. After the invention of the gas hydrates, there are 10,000 gigaton methane is available in the earth. This is a huge amount. And also we know methane is the second most important greenhouse gas, and accounting around 18% for total climate change. So there is high demand to successful utilization or value addition of methane. In the bottom, I am showing the industrially methane is using to make hydrogen. Via steam reforming, you can see here, methane plus water to give CO plus 3H2O, and very small amount of using for some other acetylene or something. But the methane can be transferred to other value-added product I am showing here. These are the partial oxidation. This is important because here this is the only exothermic reaction where we are getting syngas or H2 CO is 2:1. This is the ideal for the downstream methanol synthesis. And also another is di-reforming methane plus CO2 to give CO and hydrogen. And this is the important reaction because there are two greenhouse gas, methane and CO2 is giving syngas. And also there is oxidative coupling of methane. Methane is directly converting to ethylene. But these are not commercialized so far because there is problem mainly for the catalyst deactivation. I will talk today mainly on partial oxidation, dry reforming, and oxidative coupling of methane. The partial oxidation, there are lots of reports in the literature for the partial oxidation of methane, but the main drawback is either you need very high temperature or the conversion is less. At the same time, the major problem is the stability of the catalyst. You can see most of the cases, catalyst is highly deactive. So last 10 years I am working in this area and have several patents also, including some publications. Initially, we saw that platinum on ceria, it is stable up to 100 hours. Then we develop a catalyst, nickel on ceria, which is also highly active, but after 100 hours, it is also deactivating. Today, I will talk mainly the mixture of platinum, nickel, supported on ceria, which is very active even after 500 hours, and the temperature is 700 degrees centigrade. In catalysis, the preparation of the highly stable and also DGR catalyst is challenging. We have prepared the catalyst via sulfothermal method, including oxalic acid. We are using very nickel loading different 1%, 2.5%, and 5%. But platinum, we are using very small amount, 0.5%. This is the XRD here. It is mostly showing the structure of fluoride, that is ceria. That means either platinum and nickel are very small, cannot be detected by XRD. And here also, if you see closely the XRD peaks around 28, you can see that the peak is broadening. At the same time, the peak is shifted towards from the origin to the value. That means platinum and nickel is incorporating in the ceria lattice. Then we have characterized by TPR, we can see here, and also we have done some Raman. From the Raman, we can see the D band is shifting. That means nickel and platinum incorporated in the ceria lattice. We have done the expert study. We can see here that for platinum 2.5, where you can see that ceria 3 plus has concentration is more. That means we have more vacancy site in the catalyst, and from the oxygen spectra, you can see that the peak at 529.1, which is the lattice oxygen, and the peak 532.2 is attributed to the defect oxygen species. We have found that in our catalyst, we have more defect sites, and that is the active phase active phase on the surface for doing this reaction. This is the catalytic activity result. You can see that our catalyst even active at very low temperature, 300 degree, it is showing around 20% conversion. And also with increasing temperature, the conversion is increasing, and we can see here at 700 degrees centigrade, we are getting almost 100% methane conversion. And also we can see here that there is a linear relationship between the activity and the conversion. Then I am coming for dry reforming methane. There is also several reports in the literature for the dry reforming of methane, but the main problem here is also the stability. We are also working in this area, and we have also developed several catalysts, also patented that. Initially, we tried with a nickel supported on magnesia, zinc. It is almost stable up to 100 hours. Then we added small amount of palladium, 1.2%, and it is showing almost 200 hours stability. And recently, we developed a catalyst, very small amount of platinum, 0.5% supported on Syria, this is almost stable up to 700 hours. This is the XRD. We have done reactive feed analysis and found that platinum and nickel has gone inside the Syria lattice. And also we have done oxygen TPD here. You can see here that the second region means there is some weakly absorbed oxygen species here, and that is the most active species for this reaction. And we call this superoxide species. And this is the TEM images of the catalyst. Here we can see that platinum and nickel is highly dispersed, and also a homogeneous distribution can be seen from TEM elemental mapping here. And also we have done some XPS. Here also you can see that for our 2NP Syria catalyst, we can see that the concentration of Syria 3 plus is high for this catalyst, and this is the region that this catalyst is showing very high activity. Here also we have done, we have calculated the oxygen vacancy site here. You can see that oxygen 2Y here, that is the defect oxygen species present in the catalyst, and this is more for this 2NP catalyst. That means this catalyst is the most active catalyst among the other catalysts prepared for this reaction. Also, we have done some Raman spectra. You can see here from the Raman, you can see that the F2G band is shifted. That means platinum and nickel has incorporated in the serial lattice. Not only that, this catalyst is making more oxygen vacancy site. You can see here we have calculated also the ratio, and we have found that 2NP Syria catalyst is the ratio is the highest. That means it has the maximum number of vacancy sites, oxygen vacancy sites. Also, we have done some adsorption study, CO2 adsorption and methane adsorption. You can see here that CO2 adsorption is maximum in the moderate region below 500 degrees centigrade, and also methane adsorption is maximum in the weaker region. That means both the catalyst is very active for methane and CO2 adsorption for this reaction. This is the, we have done also in situ IR study. Here you can see that the band at 1162 and 1393, this is the CHXO species. And then this is the first time we saw that this species is forming during the reaction. And also we have found 1060 centimeter inverse, that is the superoxide species. This is also we have found during the in situ IR study. Okay. And also we have done in situ Raman study. Here also you can see that the F2G band is shifted a little bit. That means the oxygen vacancy site is created more here. And also we have seen that with time, in presence of the feed mixture, means methane and CO2, the intensity is decreasing. That means this superoxide species is consuming during the reaction. And also we have done the EPS study, which is also showing that paramagnetic behavior, that means superoxide species O2 minus is present in the EPS spectra. Now we have this is the catalytic activity study. Here also you can see that our catalyst is very active even at very low temperature. We have found that at 350 degrees centigrade the catalyst is showing around 15% conversion. And we have found that at 675 degrees centigrade the catalyst is giving more than 95% methane conversion and more than 90% CO2 conversion. And this catalyst is stable even 700 hours. This is, you can see here, the catalyst is highly stable here. Up to 700 hours, there is no deactivation of the catalyst. And typical, we have done this at 60,000 ml per hour per gram. That means very high space velocity. We have done this reaction. Now I am coming for my last talk, this is oxidative coupling of methane. Actually, methane can directly convert it to ethylene. At present, the ethylene normally produced industrially via naphtha cracking. But the problem here, there are several literature reports. The main problem is the catalyst deactivation and also the low activation of the catalyst. We have found that calcium supported lanthanum cerium oxide is showing very high activity for this reaction. This is the preparation method. Normally you use hydrothermal method where we use the nitrate precursors for all the cases, and we did this synthesis at 180 degrees centigrade and kept in the oven for 24 hours. And here is the abbreviation of this is the lanthanum ceria oxide. LCCO means calcium supported on lanthanum ceria oxide. So we have deposited barium supported lanthanum ceria and also the strontium supported lanthanum ceria oxide. But we found that calcium supported lanthanum ceria oxide giving the maximum activity for this methane to ethylene. This is the XRD for all the catalysts here, and this is the spent catalyst. We can see that all the XRD belongs to this CO2 and fluoride. That means the lanthana ceria are very small amount present or dispersed on the catalyst, and also from the spent catalyst, that means the catalyst is stable. We have done this reaction for 200 hours and I found that the catalyst is very stable. This is the scanning electron microscope. We can see that rod-like morphology is present here, and this is the oxygen TPD here. And interestingly, if you see that we got a peak in the moderate region here, and we say that this is the region where the probability that there is the oxygen vacancy, we call this superoxide species, is present in the catalyst. And also, if you see here, calcium supported lanthanum ceria oxide is showing the maximum oxygen desorption peaks, that is 3.37 cc per gram. And also we have done hydrogen TPR, which is telling that the catalyst, reducible nature of the catalyst, and also here we can see that this lanthanum calcium supported lanthana is showing 3.321 cc per gram hydrogen uptake, and this catalyst is showing the maximum activity amongst the others. This is the X-ray spectra. Here also we can see that the concentration of ceria 3+ is maximum for calcium supported lanthana species. That means we have more oxygen vacancy site present in the catalyst, and that is the region this catalyst showing highest activity. And also we have calculated the oxygen 1 spectra. You can see here the different concentration of oxygen. This is here, and we can see that here calcium supported lanthanum cerium oxide is the this is the relative oxygen, means this is superoxide species O2 minus and O2 2 minus, and this is the O2 minus is the lattice oxygen. So we can see here that the presence of lattice oxygens is less for other catalysts, but for the superoxide species is more for the calcium supported lanthanum oxide, and that's why it is showing maximum activity. And also we have done the CO2 TPD here to check the basicity, and also it is showing that this is showing a linear relationship against the oxygen uptake. You can see here this value. This is the total basic sites is maximum for the lanthanum supported calcium supported lanthanum cerium oxide. And so we have done the in situ Raman. You can see here this is ceria, and the additional peaks due to the presence of oxygen vacancy. You can see here this is showing that catalyst with the incorporation of a basic metal, the oxygen vacancy site is increasing. And also we have done some in situ drift study. Here here you can see that there is a peak at 1065 centimeter inverse and also 856 here, and these are the two bands confirming the presence of superoxide species O2 minus and O22 minus, and these are the active oxygen species and doing the activity for this catalyst. And also we have done the EPS study which is showing that the this superoxide species is present on the catalyst. And this is the catalytic activity study. We can see that we have done the reaction between 600 to 800 degree, and we found that 650 degree is showing the optimum conversion and selectivity. And compared to when we are going to a higher temperature, we are getting more CO and CO2. And also we have done this reaction for 100 hours, and we can see that the catalyst is stable even after 100 hours. This is the typical reaction condition. We are using 15,000 space velocity, which is very good, and normally we are using 0.3 gram catalyst for all the reactions. Also, we have done some DFT calculation, and here we can see that the calcium supported lanthanum cerium oxide is due to presence of oxygen vacancy. You can see here the oxygen vacancy formation energy we have calculated, and this is the minimum for this catalyst. That means this catalyst is showing more activity for this methane to olefins, methane to methylene reaction. And finally, the conclusion: platinum nickel supported on ceria formation by one-step citric acid combustion method showed almost 100% methane conversion and 100% selectivity for the syngas for partial oxidation, and this catalyst is stable for 500 hours and without any formation of any graphited coke. And for the dry reforming, we found that 2% nickel, 0.5% platinum supported on ceria is showing around 86% conversion and more than 90% CO2 conversion, and we found that it is showing 100% selectivity for CO at 675 degree, and this catalyst is stable for 700 hours. And in situ drift Raman's study revealed that the consumption of surface reactive oxygen species generates oxygen vacancy, where CO2 gets activated and dissociated into CO and O star to generate the surface reactive oxygen species. And for the oxidative coupling of methane, we found that oxygen storage capacity of the catalyst improved the activity of the catalyst for this reaction. The high performance of the oxygen coupling of methane reaction is caused mainly for the presence of superoxide species, which is the active species for this reaction. And finally, I would like to acknowledge my students Rajiv, Rubina, and Rohan, my collaborators, HOD, Director, Funding Agency, CSR, DST, GAIL, NTPC, and finally my collaborators. Thank you.
Yes. One short question, one or two. Yes, finished in time. Yes, yes, why not? Yeah.
Yes.
You mentioned about 18% of methane, which could be another contributor. Where this estimation comes from? It
Actually, some data I got.
right?
Old data.
Because I heard also that ice cap melting
Yes,
might
yes.
release further methane.
Yes, yes.
Does it include that?
Actually, the data for 2018. This is old.
Okay.
Data. Maybe recent data can change the data.
Okay.
This is literature data.
Building has started long before.
Yes, yes.
One thing, sir, you have mentioned that superoxide, you have shown some data. You showed that superoxide, if you have in a sample, if you have more superoxide, it is giving you more product. So like
Actually, actually thing is that, you know, Syria is the redox catalyst, okay? So it can absorb oxygen, it can remove oxygen. Now, what we found that if you make Syria 3 plus, if you reduce that, automatically one oxygen vacancy clears, okay? That oxygen vacancy can be filled by molecular oxygen, okay? If you have molecular oxygen, that molecular oxygen can dissociate on the vacancy side and can make that superoxide species. That means that oxygen can be easily available for the reaction. So what we have found that during DRIP, IR and Raman, that this type of species can be found in this catalyst.
They can be more giving you product.
Yes, at a more active oxygen species, we can say.
So it's a wonderful talk on catalyst reforming characterization at high temperature, very insight study, and we really thank you for that. And I request to give usual acclamations for his wonderful talk. Great, thank you. Well, we have the next lecture. By Professor Hegde, who is presently a professor at Center for Advanced Research and Development, CARD, Christ University. He has successfully worked as a postdoctoral fellow at the Hong Kong University of Science and Technology, and his area of research include carbon nanosphere, supercapacitor, bio-waste and sensors. Remarkably, he has worked on, he's been recognized top 2% scientist from Stanford University, that list that we have seen last year, apart from the various other reputed awards which he has received. So Hegde has been a part of several reputed research projects and around 200 publications to his credit, and with high citation index of 4173, citation and H index 36. So, Professor Hegde, your time is 25 minutes.
So by the time Professor Hegde started, our previous speaker, he has to leave because of some meeting.
He has to leave. I also have to leave. Huh? Please. Subal, yeah, you're in a hurry to go. Pune? Or where? Please.
Thank you, sir, for the wonderful presentation. Now, I would like to request Professor A.D. Sawant, sir, to felicitate our invited speaker, Professor Raja Rambal.
Come this side so we can It's okay.
Good afternoon, everyone. Thanks to the Amity University Conference Organizing Committee for inviting me here. This talk is about agricultural crops to mesoporous nanocarbons. Professor Sawant already he is into waste to energy business. So it's directly related to how to convert the waste material into a mesoporous carbons. When we convert waste into mesoporous carbons, what kind of application we can think of and how it is contributing towards the sustainability. So this is our university is called as a Christ University. We're having nearly 35,000 students, where more than 1,200 students from foreign countries. We are having 6 campuses, one in Noida, which is very close to here, one in Delhi, one in Pune, Lavasa, and 4 campuses in Bangalore. And these are the, very quickly I'll go, these are the major equipments present at the university. We are having FESCM, IDAX, Raman, and so on and so forth, and it is available to outsiders also. They can come, and we are charging very nominal for these things. So when you are saying the sustainability, this is the very recent data about Global Innovation Index. You can see that India is, you can see here, our global innovation value is much higher than the European global innovation, recent data. So the India is growing extremely fast in innovation. Ever since, if you take the 5 years old data, Indian Innovation Index was very less, but now we are competing with many European countries and also many African countries. Even we are better than the Russia in terms of innovation. Having said innovation is there, you can see that our funding is much less compared to United States and China, almost 10 times lesser funding compared to our innovation. So that's why we need funding as well as innovation should increase. But to do that, we have to satisfy the sustainable development goals. These SDG goals should be there. Whatever research we are doing, we have to make sure that, as Professor Upadhyay already told, how we have to contribute towards these kind of sustainable development goals. So the net zero, we make sure that all our research should go to these 17 important sustainable development goals. This side, yeah. Yeah, this video is not playing. The idea of this video is, if you are sitting in front of your computer in 1980s, or if you want to use all your gadgets here, like your photo, calendar, the fax machine, and telephone, whatever the gadgets you take, if you are sitting in 1980, you don't have any space to write the notes. But 1980s, when laptop is discovered, all the gadgets which I mentioned here went inside the laptop. And now you can see, if you want to carry all these gadgets which I mentioned here with you, you have to carry 250 kilograms of luggage with you. And today, 250 gram of mobile is carrying your 250 kg of luggage. We never ever imagined within 35 years of span, so much drastic digital transformation took place. Today we are carrying 250 kg of luggage, that is only 250 grams, mobile is taking care of that. So that much changes happened. So why it's happened? Because the material becomes smaller and smaller. When it is nanoscale, it has a big impact. But again, the problem is the evolution of education. What kind of education system today we are having? It's a very beautiful slide. You can see in 1970, when education was there, the problem is given to the students. Calculate the surface area of the object. You can see object is not a rectangle, and there is a big cut here, small cut here. It's not easy. If you are not innovative enough, if you are not strong in mathematics, you cannot be able to solve this problem. But 1985, we simplified the problem. Calculate the surface area of the rectangle. We already told it is a rectangle. So this part is gone. In 2000, we again simplified. Calculate the surface area of the rectangle, multiplying the length by the width. Formula is also given to the students. If they are reasonably good with mathematics, they can just multiply this by this. They can get the answer. And 2010, that's where the multiple choice questions started coming. What is the surface area of the rectangle? 4,000, 600, 800,000. If you are good in mathematics, they can easily write this answer. It's a multiple choice. In 2015, even worse, what is the surface area of the rectangle? Michael Jackson, Canada, 600, breakfast. Student has to choose one from these things. In 2018, color the rectangle with the color you prefer. Constantly, we are degrading our education system. We are not giving the challenging problem to the students. On the other way, we are telling that we have to make innovation to the society. So these two things should have a negative impact, because we need to innovate, but we have to implement that in our education system. That's why the innovativeness we have to carry out throughout, then only we can able to this one. So last 5-6 years, India is doing so great in innovation. We are making so many Government of India initiatives like Make in India, Made in India, Swachh Bharat, Swasth Bharat. So many initiatives is really helping the researchers to innovate something new, and government is funding for that kind of innovation. To be worse, you can see, no, this video not bad. Then comes to the what kind of research area which sustainability development goals can directly implement. This again, the World Health Organization given this important information that humanity's top 10 problem for the next 50 years. As already told by the earlier speaker, energy is definitely going to be the biggest problem in coming years, because our population is increasing, but our energy demand is more. So our energy, availability of energy sources are decreasing. The next important problem is the water, then food, environment, poverty, and so on. And population is the 10th important problem. It's not a first 9 priority. So country like India, our population is the biggest advantage for us because we have our own customers. If we create any product in India, we don't need to depend on other countries to buy our product because we have our own customers to do that. The next is the carbon. Why carbon is very important? Because if you want to make any product from India, we have to reduce the cost of the devices because this is the big country with 1.3 billion population. We have to reduce the cost. Cost effectiveness is very important for us. To reduce the cost effectiveness, we need only the one solution is we have to use the carbon because that's cheaper compared to any other kinds of nanomaterial. When I'm saying carbon, again, there is a different kinds of nanomaterial like 0-dimensional carbon, 1-dimensional, 2-dimensional, 3-dimensional. Again, when you change the dimension, it also creates the toxicity in them. So we are mostly, our group is concentrating on mesoporous nanocarbon, so it's only spherical shaped nanoparticle we are preparing. These are the easiest approach. I am not going in detail to that. The one is top-down approach to synthesize nanoparticle, other one is the bottom-up approach. So this is the one which I am talking about nanoparticle. One example is this. You can see how it looks like. This one multiplied by 1200 times is this, multiplied by 1200 if is 1 drop of water. So that kind of small particle we are talking about. Even human hair, this multiplied by 100,000 is human hair. Human hair multiplied by 100,000 is 1 meter of house. Then again, this nanoparticle multiplied by 1 million is 1 ant, multiplied by this much is 1 small gram. So this is the kind of nanoparticle we are talking about. What's so special about nanoparticle? Because the nanoparticle can be tuned the way you want. Whatever the application you think of, you can tune it very easily. So that's why nano is very important, because other thing is nano is a multidimensional and it's a multidisciplinary field. You need expertise in physics, you need expertise in chemistry, biology, mathematics, now AI, ML, everything is added to this. This is the rich field where many heads are working together to making one product. So that makes product more attractive. So these are the applications you can think of. Think that nanoparticle is sitting in the middle and you have all kinds of application area like biomedical, textile, and everything. Put a line here, then you can see whatever the product you name it, the nanotechnology is having answer to that. That's why nanomaterials are very popular in coming years. So why agricultural crops is very important for this technique? This is how nature looks like. You can take a tree, cut this portion, you end up with the transverse section of this, which is in a centimeter scale. The cut again, you cut this portion, this centimeter becomes millimeter, then cut this portion, you end up in a cellular structure, which is about 500 micrometer. Cut this one, you end up with a cell wall structure, which is about 25 micrometer like this. Cut this portion, you end up with the fibril matrix structure about 300 nanometer. Cut this fibril matrix, you end up with the fibril structure. Then when you cut this one, you end up with the cellulose, which is about 1 nanometer. So advantages of natural material, especially for agricultural crops, is nature has inbuilt porosity in these kind of molecule. You don't need to dope any material to this kind of system. Nature has already put the porous structure in it. Only thing is how to convert this porous structure into nanoparticle and make nanoparticle into porous. That's the whole idea of working on agricultural crops. Having said that, it's a very important statement. People do not buy the technology, they buy the product. Because when we go to the market, we are not asking about, we want Samsung technology, we want Apple technology. But we are asking, we want Samsung products. So when we are making product, if you make a product for poor people, rich people anyway they will buy. They don't worry about it is cheaper or costlier. So if you cater about poor people, then you can able to cover the entire spectrum of audience. How to do that? Only way is the small particles. Whenever you work with the smaller particles, it is having huge impact on the electric field, optical field, magnetic field, whatever the field you take care, it increases 10 times higher than their efficiency. So that's why the nanoparticle is extremely important, because the small molecule can have a big opinion on that. The next is, think that nanoparticle comes into the market, everywhere in the nanoparticle. This is how the changes in future looks like. Whole sets of big industries will be eliminated because it's a very simple way of repairing. Customization is very normal. not big factories required. Affordability is easy because you can reduce the cost. Nowadays, so many nano-based devices are extremely cheap. Sensor devices are already there in the market. So many applications can be done with much lesser cost. So what lessons we learned for the over last 12 years, we are working on waste to wealth approach, especially from the bio-waste material. The first thing is selection of the bio-waste, because whenever people are talking about bio-waste, they think that any waste material you take from the atmosphere, burn it, you will get nanoparticle. It never works like that. So whenever you are choosing bio-waste material, you should have the thorough understanding of cellulose, lignocellulosic structure. What kind of percentage of silica in it? The higher the silica percentage is better for the porosity. But again, if you reach more porous structure, it again having adverse effect on the end production. So that's why what kind of selection bio-waste you have to do. The next is how to reduce the size of the nanoparticle. Because if you go more than 100 nanometer, by definition, they are not nanoparticle. It should be between 10 to 100 nanometer for major application. Less than 10 nanometer is for fluorescent related application like carbon quantum dots. The next is gas flow. How much gas should be passed? Because you are conducting all these experiments in the presence of nitrogen, inert gases. More nitrogen is again adverse effect. Less nitrogen will allow oxygen to pass through. Then again you will end up with less amount of carbon nanoparticle. So how to control the gas? How much time you have to heat? And again adsorption. You need a better adsorption in all this system. High surface area is required. What kind of surface area you are looking for? And how to control the porous structure in it, because all porous structure can be done with the control of gas flow and with the control of temperature. These are the two very important elements to get the porosity. The next is crystallinity. Most of the bio-waste material, when you take from the environment, you end up with either thermostatic structure or non-crystalline nature. But some of the natural material, agricultural crop-based material, gives the perfect crystalline structure. So whenever material is a perfect crystalline, it is having advantages for many applications like energy, water, catalysis related areas. The next, this I will skip, yeah. The next is, these kind of nanoparticle can also be used in the nanoparticle reinforced industries like defense and all, where tensile properties are extremely high when you dope with such kind of nanoparticle. Electrical conductivity can be tuned. Thermal conductivity for automobile industry for making coolants. Glass transition temperature can be optimized. Then flammability, then barrier and membrane separation properties in biomedical field. Then again for manufacturing all these sectors, by electronics, EMI shielding, many cases you can use such kind of bio-waste based nanoparticle which can be tuned easily and which can able to produce in a bulk quantity. You can able to synthesize in a tons of scale without compromising the quality. So what kind of mesoporous I am talking about? You can see the definition of micropores, mesoporous and macro. If your nanoparticle is between the border of micropores and the beginning of mesoporous, that means 1 to 10 nanometer size. I'm not talking about nanoparticle sizes, I'm talking about nanoparticle diameter. If your nanoparticle diameter is between 1 nanometer to 10 nanometer, that means it's called as a mesoporous nanoparticles. They are the ideal material. So whenever you are having such kind of nanoparticle, you don't need to worry about surface area, because surface area is always a very large for such kind of mesoporous nanoparticle. High specific capacitance for supercapacitors, better adsorption for water purification or any medical related application like targeted drug delivery, antimicrobial, antifungal related applications. Carbon dioxide adsorption for global warming related application. High porosity is inbuilt from the nature. Bulk production is easy, and most importantly, if you are taking the waste material from the environment, they are highly cost effective. How to do that? Take a bio-waste material, sieve it to certain sizes, subjected to tube pyrolysis, especially in the tube furnace with inert gases. Here we are using nitrogen. With heating and cooling cycles, with optimization, you will end up with the very good carbon nanoparticle. The next question is what temperature you have to synthesize. Subjected this kind of precursor into a thermal gravimetric analysis, you can see here weight loss is taking place, and from 400 or 500 onwards, you can see spherical shape starts forming, and when you increase the temperature, you will see that very pronounced spherical shape nanoparticle has formed. So that means it's not only the nanoparticle synthesis, the temperature also plays dominant role. You should know what temperature you have to synthesize, how to control such kind of nanoparticle. Then you should know the FTIR. The FTIR, you can see that all the natural agricultural crops contains the this kind of 650 degree, you can see the degradation. So if you synthesize nanoparticle here, you are in the safe region. So all the natural agricultural crop contains silicon peaks. So that you have to make sure whenever you are working on bio-waste material, it should give the silicon peaks. Then XRD should also show the silicon peaks like 110, 020, 240 planes. Then when you're subjected to field emissions scanning electron microscope, carbon is always present in the nature, whatever the natural material you take. Along with the carbon, you have oxygen, magnesium, potassium, all other kinds of material is present. So now you synthesize nanoparticle. I already told, it's a very few report in the world where bio-waste based material or agricultural crop based material end up with crystalline nanoparticle. You can see this is the nanoparticle synthesized at 3 different temperatures. In all the 3, you can see a perfect crystalline peak. And this peak represents the carbon. You can see 26.8 degree, which represents the carbon. So now it says that this nanoparticle is carbon in nature. As you increase the temperature, you are having multiple peaks. And these multiple peaks suggest that you are going towards graphitic structure. Maybe if I go to 2000 degree, I might end up with graphitic structures. And FTIR also suggests the same thing. Now no more silicon. It is a C double bond C, which is because of the graphene material. Because that's where you are getting the peaks at that kind of points. And Raman again suggests that you have having peak from D, G, G prime, which is for the degeneracy thing. So next we subjected to FESCM. You can see we took a very small portion from here. You can see all sizes of the these porous nanoparticle is same. It's a very uniform sized nanoparticle is formed. And you can see the carbon percentage increase from 500 to 80%. Then 700 it is 94%. TEM again says that they are not only spherical, they are also porous in structure. So next you move to the another kind of agricultural crop, which is called as a betel nut, which is supari in India. So advantage, this one is funded by the government of Karnataka. The idea is Karnataka and Kerala is rich with these kind of crops, but 95% of the areca nut production, areca nut goes for gutka production. And now government of India planned to ban this gutka production because Cancer Society of India put a case against the gutka areca nut, saying that chewing the areca nut causes the cancer. So now cases is going on. If they prove this, that areca nut chewing causes the cancer, nearly 6 million farmers will directly come onto the road because they don't have any other crops to grow. Because last 300, 400 years, they are depending only on areca nut. It's a rich commercial crop, right? So then we took areca nut. Government of Karnataka put some projects to many researchers saying that take areca nut and do some other applications. So we took this as creating the nanoparticle. Then we took nanoparticle because the tannin level in this one is extremely high. You can see here 15% of tannin is present in these kind of structures. Again, lot of OH groups here. You can see the alkaloids, tannin, cellulose, lignin. TGA is very attractive compared to any bio-waste material reported in the world so far. This is the only material which is having TGA. You can see 400 itself, you can synthesize the nanoparticle. It's a very stable material. After 400 until 1000, they are almost constant. So then we synthesize nanoparticle from 700 to 1000. You can see here. This is the raw material. But you can see surprising thing is when you synthesize it 700 to 1000, the carbon nanoparticle percentage is around 98.5, which is huge. Because people are talking about 85 to 90%, but this particular material is having almost 100% of carbon. So why they are getting 100%? Because you can see the selection of the agricultural crop. Raw material itself is 75% of the carbon. So when you subject such kind of raw material into pyrolysis, you will get around 20-25% is adding because all the lignocellulosic content will evaporate. Because of that, you will end up with very rich amount of carbon. But as an industry person, he might think that 700 is sufficient because it's already having 98%. So he can save money because if he has to go to 1000, he has to invest more money for going to that temperature and the nitrogen itself. But if you are happy with 700 degree, your nanoparticle size is 98 nanometer. But if you come to 1000 degrees centigrade, your nanoparticle size is 40. So same agricultural crop with different sizes for different application. And it's having high surface area also. The next one is we wanted to know where exactly these kind of porosity starts coming. We worked on onion based nanoparticle. We took the onion peels, which is again funded by Government of India. where we took the onion peels and we started heating the onion peels at different temperature. You can see at 500 degree onwards, you can see the very nice spherical shape starts coming, and 900,000, it's perfectly spherical shape. And again, TEM also proves the same thing. This is the summary of that. You can see at 258% carbon, we end up with 90% of the carbon. So more interesting thing in this one, surface area of 500 is 6, but surface area of onion 1000 is 2,961 meters square per gram. Again, people are talking about 1000 itself is a high surface area, but here bio-waste material is giving around 3000 meters square per gram. And this is the best material for water purification, because you can see the pore diameter is also perfectly 2.8 nanometer, which is a mesoporous. This is again, we applied for Government of India Onion Grant Challenge, and ours is shortlisted for that. We are working on purifying the industry water because of this thing. This I will skip. The then question is whether the same kind of approach holds good for all the bio-waste material, but it's not like that. Some of the bio-waste material works for soft template approach, and some of the bio-waste material works for glycosidic linkage approach. So whenever you are having material with glycosidic approach, you can use it for biomedical application. But whenever you are having soft template, you can use it for energy, water related application. So that means every biomaterial you have to optimize, and it has a different way of adding value to the society. Yeah. So these are some of the applications we did. Another 5 minutes? 2 minutes. 2 minutes, okay. So these are some of the applications we are tested in lab, and each application we have published at least 5 papers and a couple of patents here. So these are some of the devices we made from the nanoparticle for the defense related applications. So this is the nano composites we published here. Then we are also working on high tensile strength for the defense industries, almost 20% increase here. Nano fluids we are working on, which again this one, and wound healing for the biomedical application we tested on the rat, and within 14 days, whatever wound is there, we created the nano membrane, we put it on the wound, and within 14 days, it is a targeted drug delivery. Within 14 days, this wound is completely recovered. That's again wonderful application for the biomedical industries. Then again, the water purification, you can see within 30 seconds, we can able to purify all the contaminated water. And this is another interesting application from this one, this Drosophila melanogaster insect. Idea is to feed this nanoparticle to these kind of insects and to see how many days this insect can survive. But for our surprise, whenever we feed our nanoparticle, instead of dying, insect starts growing. So it's another application because it's a completely non-toxic. Actually, insects are enjoying with these kind of nanoparticles. So it's indirectly we can create such kind of system where we can make a non-toxic approach and for the applications. These are the supercapacitors. These are one of the supercapacitor we connected with the LED, which can glow 20 minutes continuously when you charge it. And this is the kitchen waste derived for the cost-effective method for the catalysis application. And this is the nanoparticle with liquid crystal for the display, like creating the mobile phones, where birefringence drastically increases when you change the concentration of the nanoparticle. We can use nanoparticle for sensors. We are working on these things. It can be used for oxygen reduction reaction, ORR approach. It can also be used for novel antimicrobial agents for creating the floor cleaner and all. CO2 reduction can be used with such kind of nanoparticle. And also future automobile, wherever carbon nanotube is used, we can replace with nanoparticle. So what is the future here? The agricultural crop is easily available in India, and bio-waste material is abundant in India. Instead of just burning, we can use it for value-added approach, which can strengthen the farmer's product, because we can tell the farmers that we can use such kind of product for value-added material, and that can align with national initiatives. This I will skip. Yeah. This again, if Charles Darwin theory really holds good, when man was monkey, earth is like this. When monkey becomes man, earth is like this. In the name of sustainability, we have to make sure that whatever the technology we are doing, we have to protect our mother earth. That's the main thing in all our research. I thank the Amity University, all my funding agency for this, also my team who are working there. Thank you, everyone.
Thank you, Professor Hegde, for a very exciting, wonderful talk, and a lot of applications you have been doing on, and coming to rescue of farmers, Thank you. Any quick question? Yes.
Sir, my question is that if PVA helpful in
Yeah, exactly. That's why you have to do the TGA, because thermal gravimetric analysis means we are shining in with inert atmosphere. We are checking how weight loss taking place. You should know which temperature complete weight loss taking place. Otherwise, also without TGA, also you can synthesize the nanoparticle, but you have to do lots of experiment, because you don't know whether 500 degrees, 600 degrees, 700. But once you do the TGA, you know that where exactly that drop taking place, where 90% of the weight loss taking place. After 500, where complete the weight loss taking place, it's a safe region, so you can directly go to 1000 degree or 800 degree. Otherwise, you have to do the experiment for 200, 300, 400. It saves your time.
It's not gradual, right?
It's not gradual.
Good. That's a very important finding, yeah.
Yep.
Yes.
I see your EDS data. I'm very surprised to see the data because what is the technique you use for the measurement? It's a SCM or
FESCM, sorry.
so
FESCM DAX.
if you see any FESCM in the world, if you measure the oxygen itself coming as a air conditional oxygen, so that cannot be eliminated. But
Okay.
in your case, you can see the carbon and the potassium only there, but no oxygen. So it is a calibrated instrument, or it's just like to
No, FACM is calibrated instrument, sir. We have a top-end machine.
oxygen is zero.
Yeah, top-end machine, it has already taken care of all those things. And again, whenever we are measuring any material, we will heat the material to remove the oxygen content.
Impossible any empirical formula. If you're trying to do the SCM, oxygen cannot be eliminated zero.
Oh, okay. Yeah.
One thing I want to, you're talking about the supercapacitance. What is the value of the supercapacitance? If a surface area is so much high.
Specific capacitance with coin cell, I'm talking about. Coin cell is about 150 farad per gram.
So better than even the bones.
Yeah. So we are working for final devices now.
And this is just like to addition for the not the government, just like to suggestion. So government already announced one city and one program for the Purnia Joule. Why not you convert into Joule into the supercapacitor or the descendant cell and give the energy to battery?
Yeah, the one of the few waste which is available with us, we are trying. And again, this supercapacitor is funded by. Sure, definitely, sir. This one supercapacitor is DST Nanomission funded. They already funded for this project. We got around 1 crore rupees for establishing this supercapacitor lab in our center. Yeah.
Do you have any solution for that?
Which one?
Parali.
Parali we never tried.
Nobody in the world can find Parali will remain Parali. Okay, so we thank the speaker
Thank you,
for the exciting lecture.
Yeah.
Thank you very much. Yeah. Yes.
Thank you all for such informative and interesting sessions. I'm sure it will be beneficial to all our listeners. I now request Professor A.D. Savant sir to felicitate our invited speaker, Gurumurthy Hedge sir, with a memento. We would now like to invite our delegates for oral presentation. Dear delegates, please note that you will be given 5 minutes for presentation and 1 minute for question and answer. I request the evaluators of oral presentation, Professor Pramod Kumar sir, Dr. Ravikant Chaube sir, and Dr. Raghuvendra Singh Yadav sir, to come on the dais.
ओके स्टार्ट प्लीज जल्दी करो थोड़ा वो 5 मिनट से ज़्यादा हो गया।
I welcome the first presenter, Dr. S. Shankara Narayan from Sharda University.
Only 5 minutes.
चलो ठीक है ओके ठीक है ड्राइव में लेवल टाइम बता दो मुझे यहाँ पर A very good afternoon, everyone. Myself, Dr. Shankara Narayanan. Today, I will be delivering a presentation on my research topic titled Green Synthesis of Carbon Nanodots and their applications as fluorescent probe for metal ion sensing. Okay, so to begin with, I would like to throw some light on the carbon nanodots. So carbon nanodots are basically a special kind of zero-dimensional carbon nanomaterials which exhibit certain unique physical and optical properties, okay, due to their finite size as compared to the bulk counterpart. And there have been various methods of synthesis which have been employed for the synthesis of carbon nanodots. Out of them, green synthesis is one of the very well-developed synthesis method because of the usage of non-toxic renewable resources. Okay, and because of this unique physical, chemical, and optical properties of carbon nanodots, they have found wide applications in several fields like sensing, bioimaging, medicine, and catalysis. Now, coming to my research work, so I basically synthesized carbon nanodots using the hydrothermal green synthesis, which involves the which involves extracting the aloe vera gel and then putting it in hydrothermal autoclave at 180 degrees Celsius for 5 hours, and then finally taking that impure carbon dots for the filtration using a 0.2 micron membrane to synthesize the pure quantum dots. So these are the pure quantum dots which are obtained after the purification. Now to characterize, to check the morphology and the size of the synthesized carbon nanodots, I performed the TE measurements which basically relieved an average size of 3.27 nanometers. And also in order to study the optical properties, we performed the UV absorption spectrum, which basically showed an absorption band at 278 nanometer along with the shoulder band around 320 nanometers. So, so further, in order to study the photoluminescent properties of these quantum dots were excited from wavelength starting from 320 nanometers to 400 nanometers. Okay. So in order to study the photoluminescent properties of these carbon nanodots, they were excited from excitation wavelengths ranging from 320 to 400 nanometers. And as you can see, there is a slight shift in the emission peak, okay, as we excite from 320 to 400 nanometers. And this is mainly attributed to the difference in the particle size present in the quantum dots, and also sometimes it is due to the different surface states or emissive trap states present in the carbon nanodots. And to check the functional groups present on the surface of the carbon nanodots, we also performed the FTIR spectrum of the carbon nanodots, which basically showed the presence of different functional groups like carbonyl or hydroxyl groups, then CC bond, CO bond, etc. So the presence of these carbonyl and hydroxyl groups contributes to the greater water solubility of these carbon nanodots, which helps in preventing the post-synthetic aggregation without any surface preservation. Okay, so these findings basically provides the evidence that all these groups have been generated by the carbohydrates or other molecules present in the aloe vera. Now, in order to confirm more about the functional groups, we also carried out the XPS spectrum of the green synthesized carbon nanodots, which actually showed two characteristic peaks corresponding to oxygen and the carbon, which are at 532.5 and 285 electron volts. So we actually deconvoluted this peak, and we got the high resolution spectra of the C1s and 1s peaks. So from that, we actually fitted, first of all, we fitted the CS1 peaks to 3 peaks, which were assigned to CC bond, CO bond, and COO bond. And for the O1s peak, the two characteristic peaks were obtained at 531.6 and 532.8 electron volt, which are attributed to C single bond and C double bond respectively. So these results, they almost exactly match with the results obtained from the FTR studies. Okay, so hence FTR and XPS studies, they together reveal that our carbon dots are actually consist of the graphite core, and which are functionalized with carbolyl and hydroxyl groups from the aloe vera. Now, as an application of the carbon nanodots, we actually use this carbon nanodots for the specific detection of Fe+3 ions. So for that, we actually took the carbon nanodots and put and mixed it with different concentrations of Fe3+ ions ranging from 0 to 200 micromolar. Okay, so it is like 0, 50, 0, 25, 50, 75, and then it is in that order it is coming down. So as we increase the concentration of carbon nanodots, so we see the fluorescence quenching, and this quenching was studied using the Stern-Volmer equation, which actually gives you an idea about the quenching mechanism. So there are basically two quenching mechanisms, static and dynamic quenching. So in the dynamic quenching, generally what happens is that the fluorophore, when it comes in contact with the quencher, it absorbs its radiation and then it quenches. Whereas on the other hand, in the case of static quenching, the quencher and the fluorophore, they form a static complex, which is completely non-fluorescent. So from the Stern-Volmer plot, we actually found the quenching constant to be just a moment. So from the Stern-Volmer plot, we actually found the quenching constant to be 0.034 micromolar inverse, and from that we calculated the quenching rate constant. And since our calculated quenching rate constant was found to be more than the diffusion controlled process, which is of the order of 1 into 10 to the power of 12, so we concluded that the fluorescence quenching mechanism which is occurring in our system is of static quenching rather than dynamic quenching, and this is attributed to the presence of various functional groups present in the aloe vera, like hydroxyl and carboxyl ions, which actually make a strong non-fluorescent complex with the ions. Okay, so to conclude, so these are I synthesized green quantum dots and I applied it for specific detection of metal ions. So I would like to acknowledge the help from masters and PhD students and IIT Delhi, IIT Sati for the TEM measurements and for the fellowship from the DST SCRB. So thank you for your kind attention. I'm sorry, I had to speed up because I was given only 5 minutes to speak.
So any student or any?
Yes, sir.
First, we will prefer at least one or two from student side. From student side.
Any student? Otherwise, okay. Why limited time, so.
Maybe you can get a
Now we can.
Yeah, please.
When you saying you have the application for these carbon nanodots,
Yes, sir.
where are you targeting these applications?
Achha, targeting, sir, actually, I'm basically targeting it for anti-counterfeiting applications because I actually got one project from the DST SCRB. So I'm currently working on that. So this is just a work which has been done by one of my...
The next question is,
Yes, sir.
what is the stability of your quantum dot? Because that's going to be core work.
Yes, definitely, that is true.
Are they have any vacuum effect or kind of?
Sir, they are actually quite photostable. Like I have kept it for months inside a refrigerator or open even. So I found that at least they have been stable for 2 months. But after irradiation, I need to check how much they are photostable because because whenever you irradiate for a longer period of time.
That's the major challenge at the moment.
Yeah, exactly. Yes, that's true, sir.
So if
Thank
no
you very
question, then Joeri will ask few questions. It's important. Because I'm working on the anti-counterfeiting and he is the right person for me to catch him.
Yes, sir, definitely, sir. Actually,
So what is the quantum yield of your this carbon dot?
sir, it is 11.5%.
Then how you will use for the, the anti-counterfeiting, what is the lowest quantum yield required for the any kind of the printing like offset, integlo or screen printing?
No, sir, I don't have any idea.
Okay, I was just to ask a very basic question.
Yes, sir.
You are working on the fluorescence, right?
Yes, sir.
So you are saying the lifetime 10 to power minus 8 second.
Yes, sir.
From where this magic number come?
10 to the power of, you mean the fluorescence
Yeah,
lifetime?
you are defining the fluorescence lifetime less than 10 to power minus 8 second.
Yes, sir.
From where this number came?
So, sir, this is the electron relaxation time whenever we...
How it can calculate to it order of 10 to power minus 8?
How we can calculate it? I think from the... you mean the means experimentally...
If you want to pass, then you can pass. Then I can ask the second question.
Yeah.
I will give the answer of
No,
the
no,
question.
I think there is no option of phone a friend.
So second is what is the difference in graphene quantum dots and the carbon dots?
Sir, sir, graphene quantum dots are, they are, I mean, as far as I know, they are...
I mean, you don't say as per I know because science is same for everyone.
Yes, sir. Sir, carbon nanodots, generally, they are more amorphous in nature. There is, if you see the core of the carbon quantum dots, they are generally more of amorphous in nature because they don't have proper structure.
So what is the gain if you are talking terms at the graphene quantum dots,
Yes,
or we are not talking about the carbon dots? If suppose we are make the distinguish, like sir asking the application.
Yes, sir.
So where you want to prefer for the graphene quantum dots and where you want to prefer for the carbon dots?
Well, graphene quantum dots, I haven't thought about it, frankly speaking.
Okay, I
So,
passed
sir,
the,
definitely I will explore this possibility. Thank you for
then
this.
I asked you other two.
No, I think. No, I think.
Sorry. Hello. You told about a green synthesis and about hydrothermal method. So may you tell why hydrothermal method you think it is a green synthesis method? Hydrothermal method is a green synthesis method. Are you thinking?
No, means hydrothermal in itself, it's not a green synthesis. But since I've used the aloe vera as the biomass, so therefore I'm mentioning it as a hydrothermal green synthesis method. Otherwise, hydrothermal as it is, I won't call it as a green synthesis method.
It is not green.
No, it's not a green synthesis.
It is an environmentally friendly method. Is it an environmentally friendly method?
Well, I won't say no, because after all, we are actually generating some heat energy, and also we are consuming electricity also, which actually it's contributing.
What
to
about solvent?
Yes, absolutely. Yeah, the solvent is also there.
Is it environmentally friendly solvent which you are using?
Yes, sir. We are using aqueous solvents only.
Yeah.
So there is no problem with that.
Okay. Okay.
So, thanks, Dr. Sankara. I think I'm not going to ask question. Okay? Only one question, maybe you can say nano type of question. If we put aloe vera in Google,
Yes, sir.
and if you put your own topic, either quantum nanodots or quantum particle, it comes 1,000 literature. So how do you sure about novelty of your own one?
No, sir, actually in this, most of the people have just, I mentioned about the dynamic and static pinching. So mostly people just stop at the level of, finding the limit of detection, and then they don't go about, characterizing the complex. So here I've actually characterized the complex, whether the complex is a dynamic one or a static one. So this kind of fluorescence lifetime series, it's not done by everyone.
Yeah, okay, thank you. I think we have to give, let us give a big consideration to him.
Thank you, sir, for such a wonderful presentation. Our next presenter is Dr. Krishna Kumar Pandey from Sharda University.
Give me. A very good afternoon. Very good afternoon to everyone. Myself, Dr. Krishna K. Pandey from Sharda University. I belongs to Acoustics Research Laboratory, School of Basic Sciences and Research, Sharda University. I am very much thankful to the convener of this conference, Amity University. The topic of my presentation today is novel synthesis and ultrasonic investigation of aluminum oxide xanthum gum nanofluid. I know, and I promise to take care of 5 minutes, so I will not take much time. This is our campus view. I am not going to read the things line by line. The thing what I want to focus today, I will be highlighting simply. So what we people are doing in our acoustics research laboratory is that we are doing several things. We are doing non-destructive evaluation, you can say non-destructive testing with several type of binary liquid mixtures, several type of organic mixtures, several type of solvents we are using. We are doing polymer solvent molecular association study also at different temperatures, also by varying the ultrasonic frequencies. In our laboratory, I will be showing some glimpse also. My area is acoustics. So acoustics is a well-known branch. I am not going to read anything line by line. I will be simply highlighting the results to make the time foundation. This wheel was developed by R. Bruce Lindsay, and everyone, my dear, I can say some students from Sharda University are also here, and all the respected delegates and all the respected dignitaries. I just want to make a focus that acoustics, it is involved in several, almost all the areas, life science, arts, oceanography, engineering, we are doing in all the areas. It was developed by Professor R. Bruce Lindsay. Actually, we people are much aware about doing SEM, TEM, FTIR, AFM, FE, SEM, XRD, all we are doing. But in our laboratory for characterizing the polymer nanofluids, polymer solvent mixtures, we people are doing some add-on by using ultrasonic waves actually. And of course, these waves are really non-destructive waves. Nanotechnology, everyone knows. And ultrasonics, it is not non-harming wave. We know having 20,000 hertz, more than that frequency. We use these ultrasonic waves for several purposes, for intermolecular interaction, study of liquid mixtures, evaluation of thermodynamic parameters of liquid mixtures, study of miscibility, pharmaceutical industry, we are using it, for several food industry, we are using it. We are searching the formation of several new liquid mixtures, their miscibility study we are doing. And there are several applications. I am having so many slides, but I will not go through. And these are some basic formula. I will be showing the machine which I am using in my laboratory, that is ultrasonic interferometer. The basic parameters for further calculations, more than 15 parameters we are calculating in our laboratory. So ultrasonic velocity, my machine ultrasonic interferometer gives us. Then we calculate several another parameters. This is some outer view of acoustics research laboratory. Outer view I cannot say, the inside view, one machine I am showing. There are two cylinders I am having. I am doing comparative temperature study, comparative different ultrasonic frequency studies. Two ultrasonic cylinders we are having, 2 megahertz, 5 megahertz in our my laboratory. And some methodology we are having. What is the main thing I want to focus? Yeah, so xanthan gum is a polysaccharide, a complex sugar that is commonly used as a food additive. It is produced through the fermentation of sugar by xanthanus. The resulting compound has unique whatever. So these are there are several you can see about it. And first of all, I must acknowledge my student. Basically, this work was near about done by him. This nanoparticle was prepared by him. Then we have done this. Yeah, yes, sir. Then we have made this polymer nanofluid called aluminum oxide xanthan gum. And then these characterizations we have done due to shortage of time, only the specific ultrasonic studies which we have done in our laboratory. I am showing the first graph. You can see ultrasonic velocity value. As we are increasing temperature, we are getting some value increasing like that, and density, then whatever another things you can see with temperature. And compressibility value, you can see the method, the nature of the graph with temperature from room temperature to 60-65 degrees Celsius. We have done it. Some samples. And the last, some conclusion I can say, the synthesis, the synergetic effect of Al2O3 and xanthan gum in the nanofluid formation might lead to enhanced thermal conductivity, stability, making it a promising candidate for the heat transfer application. Actually, the combination of these materials could potentially address challenges in heat exchange systems, offering improved efficiency and performance. These are some recent publications, some references, some recent publications from my laboratory. My students have done for several ultrasonic investigation, physicochemical behavior study for stars recently. It was published in Journal of Physics conference series. I am so much thankful to everyone for patiently hearing this session. Thank you very much. Thank you.
Now I think we can allow first of all from student side at least 1 to 2 questions from student side.
Yeah, I will be happy, and I really invite everyone present in this ORD for open collaboration. We can do ultrasonic study. This is one add-on area for all the other nanotechnology areas. I really invite every respected delegates, professors here also for future collaboration.
So if no question, I think we have to, sir is going to ask
Sir,
question.
sir, please.
Yeah, Neha, one. Sir.
Yeah, of course, and we have done it. We have made this polymer nanofluid, and I know you belong to Sharda University itself. So I offer you also that in coming time you can add on this work with your coming publications. We have the sample in our laboratory. Of course.
Yeah.
Thank you very much.
No.
Sir. Sir. Right, sir. Yeah. Yeah. Sir, I am very happy to answer this question. Sir, actually, here in our country, since last 5 to 10 years, there are several suppliers. They have developed several ultrasonic machines. In my laboratory, I am having the machine which is dedicated for liquid medium only. And I am having the cylinder this like shape, and the quartz crystalline is in the base, and we are simply using piezoelectric effect to generate the wave. One probe is there, and we are circulating water to maintain the temperature. So the machine is dedicated for liquid medium, but of course what you are selling, that may be done in future, sir, may be done. Yeah. Yeah, sir. Sir, definitely we can. Definitely we can, sir. Yeah, and I'm also looking in that direction with coming time with your blessing and collaborations that we can develop such things also, sir. It will be a nice area to work, sir. Thank you, sir. Thank you very much, sir. Yeah, okay, sir. Thank you, sir. Thank you very much, sir. Thank you.
So worldwide already people are doing for the acoustic spectroscopy.
Sir.
So their resolution is more than the optical resolution.
Yeah.
So already in the world. Yeah. So you are very nice question asked. But
Definitely, sir.
I will ask very
Please,
basic
sir.
question because many students are there. They will more, knowledgeable if, you are using the AL203, right?
Yeah, sir.
And you mentioned the BCC and the FCC. So what is the role of the crystallographic those structures?
Yeah.
So they deliver the ultrasonics, that frequency.
Definitely.
Can you connect both?
Definitely. Sir, actually what is happening is that we people, we are able to do such study for theoretically also. So I am having one program, we are also doing with BCC, FCC structure
I am
also.
asking the logic behind that.
Yeah.
4 coordination, what is the logic?
Yeah.
If suppose the 8 coordination, what is the logic? If suppose the SCP 12 coordination, what is the logic?
Definitely.
If suppose the primitive, then what is the logic? I don't want to what the theory or what the software using.
Yeah.
Any science you can contribute here, what kind of the science connected with the coordination number versus the frequency.
Yeah.
I will be happy to that answer.
Sir, actually right now, till now experimentally we are not doing those things you are asking. We are doing theoretically those things actually. But here in our polymer nanofluids, we are doing velocity measurement by using ultrasonic technique actually.
Okay, I can
Maybe.
ask you one more.
Maybe,
question
yeah.
Because by nature to know,
Sir, it's our pleasure, sir.
gain my knowledge.
Sir.
I seen last many years, at least 20 years, I seen the ultrasonic society and a lot of things are going on.
Yeah.
And till date, people are using the quartz crystal for the frequency generation.
Definitely.
And a lot of stain generation nano generators are coming in the picture in the science. So can you tell me what is the most next suitable to quartz?
Definitely, I can answer. Sir, there are most 3-4 examples I can say. Calcite crystal, quartz crystal, tourmaline salt, Rochelle salt, we can. Yeah, tourmaline crystal, sir, it is having a specific X cut, Y cut. So if we want to generate the wave in particular direction 111, 110, then we can use tourmaline crystal for that also.
Then why you don't know the BCC and FCC?
Sir, actually, yeah, no, yeah, you are right, sir. Actually, yeah.
So, okay.
Thank you, sir. Thank you very much.
Pandey, thank you.
Thank you very much.
Give a
Thank you
big
very much.
clapping for at least this nice presentation.
Thank you so much.
And I request all of students, if you have not courage to listen, or maybe don't put here for gossip only. This one is giving very bad impression. Please do not remind me, otherwise I am coming also COE farm, controller of examination farm. It's not good scene. If someone is going to present in front of all of you for your better future, if you do not want to listen, go outside, it's okay. We will manage. So please do not bother me to do these kind of things. Okay, with this one, I think we have to going to invite our next presenter.
Thank you, sir. Indeed, a very delightful presentation. Now, our final presenter for technical session 1 is Dr. Harmohan Singh from Sharda University.
A very good evening to all of you. My name is Dr. Harmohan Singh. I am presenting here insights of algal biomass-based biomaterial. As you know that Professor Harimohan Upadhyay sir already told about what is the global warming, what is the climate change, what is the scenario, and how to achieve the net zero emissions from different countries. In India, around Indian target is 2070 for the net zero. These are some problems that is you all know what is the problem. Yes.
5 minutes.
Okay. I am concluding. As you know that population growth basically elaborated the urbanization, industrialization, and fossil fuels and environmental health and hygiene issues in currently. And these issues are basic challenge for the human life on the earth For these, human life basically survive on the base of the plant-based material or plant-based food materials, or maybe you people say that plant-based fertilizers, plant-based fuels. And for this, one of the organism name is microalgae. That is basically in morphologically there is two types. First one is a macroalgae, second one is a microscopic algae. Here I am presenting just the microalgae. It is a very sophisticated organism that required to sequestrate or biofix the environmental CO2 in the form of the biomass. That biomass contain various chemical elements that is important for the human life on the earth. These elements basically, these are some pictorial pictures. These are the basic mechanism that sequestrate the environmental CO2 in the form of the biomass. Here there are two aspects is given. One is the CO2 from the normal atmosphere, and second one is the thermal based power plant, that is basically in the term of the flue gases. Okay, and these are the basic composition of algae that is described by various scientists, and one of my study is also elaborated here. You people can see chlorella, one of the prominent algal species that contain more than 40% protein and around 25% of carbohydrate and around 20% of the lipid. This lipid can be easily converted into the biofuels via transesterification processes. And as you know that biorefinery aspects basically produce various products that are important for the human life. And what are the application of the feed and fuel of algae on the earth? These are some algal species that required for that is basically used for the fuel and feed applications. And these are the sub algal species that is basically currently used in the human daily lives. One of the algae name is spirulina. That is basically drink form utilized for the sportsmen and normal people for the protein and carbohydrate requirements. And after this fertilizer and Nostac and Anabina, some kind of blue-green or cyanobacterial species that are required for the fertilizer applications. These are some basic mechanism that produce the fertilizers on the earth. And these are the fuel application. Here most of the energy, as you know that around 60% energy comes from the thermal based power plants that are basically utilizes natural coal, and these natural coal basically produces the CO2, that is carbon dioxide, that is the one of the main reason of the global warming on the earth. And this carbon dioxide can easily sequestrate or biofix into the biomass by the algae, and this algae produces various kind of bioproducts that can be utilized for the feed for animals, fuel for the vehicles or automobiles, food for the human health and medicines, and fertilizers and other applications. Okay, and these are the some basic efficiencies of the some microalgal species that is given here. And these are the microalga, basically seaside algae and freshwater algae that is sequestrates the CO2 on the different kind of media concentrations. And conclusion is basically algae is one of the magical organism that produce for the various kind of application, basically fuel use such known as the ethanol applications, and protein for the spirulina, chlorella. These are the basic species. And algae can easily grow in the wastewater. That means it can easily treat the wastewater. That is very novel or sustainable approach that not required any energy from the external sources, and produce the valuable biomass that is a source of the energy and other applications. Thanks to all. And these are some references that are used here. Thanks.
So we are again going to start with the student side. Please do not feel angry. This is common nature of any teachers. You can say, if you have any question, this one is a nice chance. You have to ask this, Dr. Harmohan. I think no one is agree with us. Okay. So
anyone, please.
Yeah, I think then I think Bipin is going to ask.
एक्चुअली एनपीएल के बगल में आईआरआई है, तो अब क्या करते हैं, ब्लू एलगी का भी थोड़ा एक्सपीरियंस है हमें.
यस सर, यू कैन.
आपने कोई लाइट की जरूरत नहीं है एल्गी को ग्रो करने के लिए। स्टेटमेंट करेक्ट है आपका?
No, sir. There is requirement for the photosynthesis purpose. Light and CO2 is compulsion.
Yeah, otherwise you cannot.
Okay.
Then if you want to convert into any fuel, you are just to projecting here, you listen these application can possible, or you have done any one?
Sir, actually, I have done basically lipid conversion by the transesterification into the FAME, that is fatty acid methyl ester. That is the one of the forms.
So I just to summarize is because we have the less time. So what is the energy balance to convert into any fuel by this biomass? I mean 1 kg में आप कितना convert कर सकते हैं?
One means
1 kg biomass से I mean algae लेके आप कितना convert कर सकते हैं energy?
Actually, sir, in currently in simple nutrient conditions, basically algae produces around 20% of lipid. A lipid can convert into the biofuel. Listen, and if we produce some stress condition, that means stress condition basically stimulate the biochemical reactions into the algal cell. That stimulation basically evolve some kind of catabolic reaction into the cell, and this catabolic reaction basically produce more than 30% of lipid in the algal cell. In my experimental, basically in my PhD, I have achieved 21% of the lipid, and this lipid can easily transesterify into the FAME, that is a fatty acid methyl ester, that is well-known biodiesel, well-known form of the biodiesel. It means around 20% of the crude oil. I'm not talking about the purified oil. 20% of the crude oil can be achieved by the 1 kilogram of the biomass.
Then it means energy balance is negative till?
Sir, not it is negative, because during the sequestration, means during the production of the algal biomass, algae consumes...
No, don't you only see the mass, the growth area and the energy produced to grow? That is also going to cost for the conversion.
You may say, for the current available technologies.
If you have data, then fine. Otherwise, I mean, unnecessarily, why we will...
Sir, I am not going to the negative energy balance because it is my field. If you go for the LCA means, listen, sir. If you go for the LCA means life cycle assessment, where you can find the, it is not negative balance, it is the positive balance, because the total emission in terms of the CO2 is negative.
Actually, MNRE, there is a report. Okay,
yes.
There is many projects running on the algae. And one of the project from the Professor S.P. Singh from the BHU, okay, blue algae. Another project from the Jerry Imraham from the IRI. So they are trying to produce the algae to this kind of the conversion. So till, I mean, those data is you need to look. I mean, if you have done something novel, then.
Yeah, just going to.
I'm just correcting, sir.
No.
Okay.
Just curiosity, maybe not.
Yes.
We want to finish on time.
Okay, sir.
It's a curiosity. I'm not an expert in
Okay, sir.
photosynthesis. So the plants, they grow out of photosynthesis and they produce wood mass, which is again a kind of biomass. How your algae is different from that?
Yes, sir. That is good question. Actually, during the production of the biomass by the tree or large plant, basically tree plant contains lignocellulose. That means the basic component is lignin. That is, denature of the lignin is very complex. That is why that is basically alcohol. Alcohol is the fermentation of the food product, basically carbohydrate. If you have available the lignin-free cellulose, it means it can easily convert into the ethanol. But in the case of the tree plant contains lignin. That is why it is difficult. But in the case of the algae contains hemicellulose. That means it have a very less amount of the lignin. That is why algal biomass more suitable for the conversion into the ethanol as compared to the tree plants. Yes, it is better route, and present study, one of the study, basic fundamental study comes from the Japan in 1992. That is basically elaborate 1 kilogram of algal biomass sequestrate 1.83 kilogram of CO2 from the atmosphere.
Harmohan ji, can you close this session because
Yes, sir.
already...
Okay, sir. Thank you, sir.
So only I conclude this session with the comment, you can try to those algae for the Ajinomoto to grow, because chow mein is people using a lot. So that will be more useful than the fuel.
Thank Thank you all. Thank you all for such informative speeches. With this, we come to an end of our oral presentation session. Thank you all for your patience. The technical session too will start shortly. After a short tea break of 10 minutes. 5 minutes.
So I think there is a quick tea break just outside of this room, and within 5 minutes, I request all of you to gather again in this room for next session.
I now request all the dignitaries, Session Chair, Professor Rajiv Mehta, keynote speakers, Dr. B.K. Gupta, Professor Kedar Singh, and our invited speaker, Professor Praveen P. Ingole, from Department of Chemistry in IIT Delhi, to please come on the dais. We are honored to have with us Professor Rajiv Mehta, who is the head of Chemical Engineering Department at Thapar Institute of Engineering and Technology, Punjab, as our session chair. Professor Rajiv Mehta has received his master's degree from Virginia Tech Institute, US, and his bachelor's from IIT Delhi. He worked as scientist for 3 years at Wright-Patterson Air Force Base in Dayton, Ohio, USA, where he did very useful work with regard to development of graphitic forms and almost defect-free thin films for nonlinear optical properties determination for the US Air Force. He has also held various prestigious positions in India. His research interests include synthesis processing of thermosets and modeling and simulations in polymers. He has also worked in the area of chemical sequestration of carbon dioxide into high-value polycarbonates. He has developed the technology to incorporate the low dielectric strength polymers into cellulose insulating paper used in transformers. He has been conferred with various awards and recognitions like Best Innovative Young Researcher at the 4th International Conference on Nanoscience and Nanotechnology at SRM University. Professor Mehta and his co-workers have received Gold Trophy in the Plast India 2018 for the category of Best Research in Polymer Sciences, Technology and Engineering. He has guided 12 PhD students and has got many publications to his credit. I now request Professor Rajiv Mehta to kindly introduce our keynote and invited guests to deliver their talk.
Thank you for a very nice introduction. It's my pleasure to introduce Dr. B.K. Gupta, Principal Scientist and Associate Professor, CSIR, NPL, New Delhi. Dr. Gupta obtained his PhD, MSc and BSc in physics from BHU Varanasi chapter, Banaras Hindu University. With his 20 years of R&D experience in the field of experimental solid state and condensed matter physics, material science, nanotechnology, nanotechnology, and hydrogen energy storage, and its applications in hydrogen-fueled vehicles and devices. Presently, Dr. B.K. Gupta is a principal scientist at Photonics Materials Metrology Subdivision, Advanced Materials and Device Metrology Division, CSIR NPL New Delhi. His current research interests are focused on development of luminescent materials, both bulk and nano, luminescent graphene quantum dots, and 2D new emerging materials for application in luminescent security ink, security codes, optoelectronic devices, biological fluorescence labeling, fluorescence quenching, field emission displays, and luminomagnetic nanophosphors as nanoprobe for drug delivery and external magnetic tracking applications. He has got more than 200 publications in well-cited journals and has been granted with 2 patents. He has been awarded with Indo-US Fellowship Award 2010 in Physical Sciences by Indo-US Science and Technology Forum, New Delhi, and has also been conferred with the prestigious MRISI Medal Award 2018 by Material Research Society of India. He is the Vice President of Indian Association for Hydrogen Energy and Advanced Materials and is a life member of Indian Physics Association, BHU Varanasi, Luminescence Society of India, founding member, Delhi Zone of National Hydrogen Energy Board, and member of Carbon Society of India. He is a member of Advisory Board of Applied Physics, Amity University, Noida. He is also a member in the editorial board of various reputed international journals. With that introduction, we are privileged to have Dr. Gupta with us, and I would request him to please give his talk. Thank you.
So thanks to all. First, I'd like to thanks to organizer because with the MIT, I have the association long ago. Because once nanotechnology started in MIT University in 2005, when Kapil Sibal inaugurated the nano building, at that time I just came as a scholar to place of my guide to give the talk. So that time Ashutosh Sharma and the B.R. Mehta, G.N. Mathur, and my name was there, Owen Srivastava, Arrow, Dr. B.K. Gupta. And till I am still associated with this institute, I am happy to be here. And many of my friends, classmates and colleagues are also here, like Sanjeev here. So today I will discuss about very important topic because I seen last many talks and I realized that people trying to material like just like a game. Without understanding, they talked about the materials. So it is my the urge to all the people they are in the material science, they try to understand the depth of the materials. If you know the depth of the materials, you can search the real goal of the application and then can get the success. Like I am from the National Physical Laboratory and we have the mandate, 3 or 4 kind of the, like one of the mandate is to we can help the industry. So one of the work for the like Security Inc., we already transfer the technology for the currency to Government of India for the luminescent and the optical variable ink. Regarding the industrial application, we developed the blue laser induced white light for the FIAM industry. And now I will talk about today the basic science. So now people talking about the quantum materials. It's a very new name because it's very difficult to understand for the students how we can define the quantum and the nano. Because it's a big the separation between the nano and the quantum, but it's very difficult to explain if you ask in the interview or like any time. And if you go to Google, nobody will tell you the difference between the quantum and the nano. Only when you realize when you do the experiments. And that's why I chosen the topic, the quantum materials for the application for the terahertz. I will talk about the 2 applications like the quantum Hall resistance devices and the terahertz devices. So I will give these some examples, but because I especially make this few of the slides for the student, although very few students are here, but I'm happy to be share with those students to these kind of my thought. Whenever I give in my talk, always I dedicate to my guide because whatever I learned from my guide, he is the person behind me. That's why what I am here. So basically, he is the person I learned from the dedication, consistency, hard work, and the passion for the science. And he left for us because of his passion and during the COVID. And I never seen a person like him. And whenever I meet to him, I always get a new thoughts, new idea. That's why I thought it may be because of the like many years interaction with my guide, few neurons interchange with him, with me. But now this slide is very important with my students because they are always sitting like a statue. So I want to say, don't bother about any professor or any scientist or any faculty. Anyone can be scientist. Even a rickshaw man can be scientist if they observe the wonders. Like I saw something, you try to see it carefully. If you see the wonders, then listen the ideas of others. It's always gain, never the going to loss. Then conduct the experiment if you get something. And then you ask the questions. You ask the questions are very important because this is missing from the scientific community. That's why 100 years past, we are never able to get second Raman. So if you want to second C.V. Raman, you need to be asked the questions. you get the degree, but again the situation will be like that you have the PhD degree, but we go for your mobile to class 10th fail. And this is this real education system of India, and you have to accept it. So if you want to do, then you have your own choice, what you want to do. And if you use the questions, then use as a tool to solve the problem of the country. Country never pay you the fellowships or like any salary for anything else except the contribute the country. And then if you discover something, don't escape it. If this is discovery or real discovery, then explore around the world. Then only you know your discovery, or otherwise you never will make the difference between the invention and the innovation. Most of the people in the laboratory, they done the invention, never the innovation. Many things are coming in news, but never coming in the use. The reason behind that, they are doing the innovations, but inventions, but never come into invention. Why I am coming here, and what is the advantage of this? You can see the learning pyramid. If you are just to listening the lecture, just like 0% you will gain. If you are just reading, then 10%. And this is the research from the USA. I am not saying about my own learning pyramid. And this is experiment on the people, they have the average mind. And if you listen audio visual, then 20%. If demonstrate, 30%. If discuss, then 50%. When you're doing the practice, then 25%. When you teach to others, that's why I never miss the chance for any kind of the invited talk or any talk to discuss with the peoples. Then why need to quantum? Because our government hungrily need the quantum devices. A lot of money. To whom government give to this money? Who has the technology? Why they will give the money? You have the understanding about the material. You have the understanding about the device. If no, then why the money going to expand and waste? So it is very important. And government recently make a team for the 126 faculties for the 2D Materials Excellence Center in the IIC Bangalore. Fortunately, I am also the member there. And we are trying to looking very seriously how we can contribute to our country. And this recommendation going to Prime Minister, and every 6 months they are trying to review how we can go to quantum technology. And obviously our Prime Minister also saying if we have the skill, then only we can make a developing country. And then only we can achieve the trillions of the economy. Otherwise, everything just like a dream. And before I can start my talk, it is very important because I am just like a engine, but real wheels are here. Because they are contributing the science, that's why I am here. So now we can talk about the why terahertz. If you see the applications of the terahertz, hardly any field in this our system, our daily life, where we are not using the terahertz application. Even if you talk about some fancy communications like the navigations or like new technology, 6G spectrum we are looking, also we have required the terahertz. And you know the range of the terahertz. For the students, just like to make this slide, 200 gigahertz to 10 terahertz. And I am fortunately entering this field because of the fact earlier we were working for the electromagnetic radiations. And EMI shielding and terahertz very close. If you understand that part, very easy to jump in this part. And now, what is the real benefit for the nation, this kind of technology? If you understand this data, how much gaining British by the communication. So same we can get from the India because our 150 million peoples, and we have like BBC like kind of the communication center, then our gain can be better than the what they have. So we can contribute to like 5 trillions by this way. One of the way to we can generate the terahertz devices. Another societal benefits, like we want to fast communication, we want to fast navigation. So, and other like healthcare or like biomedical, everywhere we are required the precision. So this kind of the technology can be help in that direction. And why we are looking the 6G, you can understand, because our modern society is fancy for the two things, like speed and speed and speed. Desire is not endless. And another is like the how much precision for the navigation. If both things we can control many things. What kind of the material we are trying to see and why we are talking about the 2D materials, that I will connect here, and why we are talking the term as a quantum materials. So if you see carefully, we are talking about the, if you want to source or detector or like modulator, you have required the 2D materials. Why these 2D materials? Because 2D materials, one advantage is like the confinement is one direction, and second advantage is like flat surface. Third advantage like previous speaker saying like if you change the dimension, increase the toxicity. It's totally wrong statement, because I am the very blunt. If anything wrong, I can say the wrong anywhere. I can logically answer to why I am saying this statement. So if it's a 2D, it's nothing is going to toxicity, because why people are working for the 1D to toxic, because a tubular structure or like rod-like structure. That's why European Commission putting their report to, if you're using like carbon nanotube or like rod-like structure, it can rupture the cells. So that's why people thinking about the either quantum dot or like 2D materials. So why we are choosing like the MOS2 or like the graphene? The reason behind that, because without logic we cannot accept the science. So you can see here, if you see the property of the graphene or like MOS2, what we are looking in these materials, when we are talking about the monolayer or like the single layer, then we are talking about the confinement. When we talk about the confinement in one direction, it means if you are putting the any energy or any frequency, it means if you excite the valence band, then electron will energize and come out the conduction band. Once it come out the conduction band, and if suppose it's like the one dimensional, it means confinement in one direction, it means the electron is going to entangle. It is not free like the 3 dimension or 1 dimension or other dimensions. So that is the reason people looking for this kind of the material. It's required the mega electron volt. And if you see the conduction band quasi-particles like the exciton, bi-exciton or trions, their energy is also in milli-electron volts. That is the suitability why people talk about nowadays the light matter interaction. Otherwise, people when talk about the quantum dots, they directly talk about the direct band gap. They only talk about the photon, but not take out the phonon or like electron and photon interaction. So now people now talking about the electron-photon interaction. So this is the best example you can see why we are looking the another material after the copper, because if you see the comparison, the 2D material like graphene, if you see the example, there is a wide range of the frequency, as well as another advantage is more the EBI, electromagnetic shielding, absorption. So these two things make more suitable than the existing material like copper. So that is the reason it's collectively, if you see the distance covered from the copper, it's like the millimeter or like some meter. But if we talk about these kind of the milli-electron volt kind of the system like the 2D materials monolayer like MOS2 or graphene, we can change the range like the kilometers or more than the 1,000 kilometers. So that's why communication, it is very important. And that's why if you see this Nature article, and particularly what I am saying, already they mentioned here the action is of the collective electrons, not the independent electrons for the quantization. So how I realized this experiment, I can just to give example of one of my students' work. So they trying to make the MOC2 by the CVD technique, and what we realize, if you see the literature, in Nature one paper they are saying the direct band gap 1.5, another saying 1.58, another saying 1.54. We were surprised, a lot of papers in Nature or Nano letters are good journals, why their band gaps are different. Then we realized that because of the quasi-particle presence and the condition of the quasi-particles are different, that's why we realized that the different kind of the band gap. Because the quasi-particles, if suppose exciton, then it's contribute like milli-electron volt. If suppose that contribute like the bi-exciton, then 100 milli-electron volt. So band gap drastically changed from the 1.50 to 1.58. So I will go to details, but before that I will just to compare with the nano and the quantum, because it's a very important. This is a very traditional, everybody is showing, so I will not go to this slide, and quickly some slide I will cut. So advantage only I will show the nano. Why? If you really talk about even the nano, then you try to understand the difference between the bulk and nano is 4 things. One is if you talk about the nano, the gravitational force becomes negligible, and if you talk about the electromagnetic force, it's going to dominate. That's why most of the nano or quantum materials people using for the these kind of the applications. Second basic difference is they deals with the quantum mechanics, not the classical, but it's already in the literature, I think people, and greater surface by volume ratio. So these things are and fourth is the random motion in case of the nano, but in the bulk it's a gravitational pull. So these fours if you know, then you know about the nano, but again you want to beyond the nano, because these things are the thermal property, mechanical property, electrical property can be changed if you tailor. But if you talk about the beyond the nano, then what I said about the you have to understand the conduction band transitions, and small transition you have to keep in mind. Otherwise you cannot understand the difference between the nano and the quantum. So if you see here, like one cell, even it can be called as the nano if suppose there is no quantization in the conduction level. If suppose there is no sub-level splitting in the conduction band, and we are talking about the direct band gap. So if you see the literature of the Victor Kilmov article, or like Bawandi article, which is recently getting the Nobel Prize, so they talk about why the difference between the quantum materials and the quantum dots. So if you understand this kind of the logic, it means if surface convert into volume, it means we can say the nano, but it is not the quantum. So quantum means is different what I am saying. So if you see the even characteristics, you can get the same like what the difference in the bulk and the nano. Same it may be you get for the quantum, but the realization you require the specific tool. That I will explain later on how you can realize it. Like nano, I no need too much to explain here. All of the students in their childhood, they already make the nano materials, because as very carbon, if you heat it and it convert volume into surface, and they make the carbon nanoparticles. So just like to putting the understanding for the nano and the difference from the quantum, I just putting few slides of the nano here. Like if you saying the quantization, you understand from this slide, it will be more better than the other slide I can explain. If you see here, if talk about the nano, it means splitting the sub-levels. But if you talk about the quantum, then again you have to talk about the sub-level transitions. Only sub-level transitions, that energy is going to interact with the direct band gap energy. So that is the big difference between the nano and the quantum. We could talk about the only quantum, then we have talked about the splitting sub-levels, and we are talking about the direct band gap. So you can try to understand between these two terminology. Till date, very few literatures, like one Nature Physics article already I shown here. So if you see the confinement, like I told about that, if 0D, then it's confinement in all three directions. If like 1D, then two directions. If 2D, then one direction. If 3D, then question will be coming from the peoples, like why 2D is so much late discovered. The reason behind that, when the 1D discovered, then people think like that, if suppose we can confine it in the 3 direction, then we will get the more benefit. They are trying to discover, but unfortunately, they are not able to make this table, what the Professor Harimon told earlier. Then people realize that we have to discover something else, and then they realize that only one material is there, that is, I can just escape few slides. So only one material is required, that is 2D materials. And why they are going the 2D, I will just to go there because it's more important to that slide to discuss. Yeah. So why 2D materials? The reason behind that, a lot of advantage of the 2D, but what is the history of the 2D? I think very few in the hall, they understand the history or know the history. Even 1937, people first proposed about the 2D, but whole analogy is going to rejected by the scientific community. And they said like, because crystal 3 direction periodicity is required, if not going to periodicity, it is not going to acceptable. Then 1947, again the single layer graphite trying to propose, but not going to accept it. Then 1962, they, Hans and Peter Bowen, they putting the terminology graphene, and then ultimately then the theoretical studies said about the graphene, and the people they discover the graphene, you will be surprised, they are not the field of the graphene. And you will be, I will just to give that a story because it's very important for the students, because they can understand in the 5 years even possible some discovery. Those people are earlier working for the geckos. They work on the geckos to how geckos are sticking with the wall. And they're trying to make some polymer mimetic, and they're trying to put the Spider-Man and trying to stick it on the wall. And how they can go systematically, you can see here, they make a polymer, this kind of the fibers, and trying to 140 gram Spider-Man, and they publish this paper. And later on, they're trying to calculate the force and everything, and ultimately they can make, they're trying to search some the natural materials, then they tried muscovite, biotite, and ultimately they discovered the graphene. Very quickly, I will just to a few minutes, I will cover the importance of the work, because I understand 25 minutes for me, it's a very difficult. Normally, I'm not trying to just to give the talk. I'm trying to put something to student they can carry in their mind. So I can just to skip all the things, but I will go to that part. I will only discuss because that is the important part. Yeah. So life is always challenge. It's very important to I can share my challenge. When I started the graphene work, we have only the furnace and purchased by someone else, and I have to ask the funding or no funding, even though we started the work and within 3 months we developed the CVD graphene single layer, and it is now commercial level to available for anyone within 5 lakhs. And we make the quantum Hall resistance devices by using this single layer graphene, and continuously from the 2017 till date. If you see the data, what we have made, because it's very important to also talk about the indigenous products. So you can see any data, if you correlate with the like nature or science, our data is much better for the single layer graphene. And we are making like 2 inch by 2 inch or like 4 inch by 4 inch. And after making the graphene single layer, we went to TFR Mumbai to test the device. Whenever you are trying to make the material, you need to understand the material. Again, always to repeat this sentence. So we started from the first mechanical exfoliation, try to understand the pure graphene. And then we try to understand single layer, bi-layer and tri-layer, and why it's going to single layer, bi-layer and tri-layer. And then we can try to understand how the product which we are synthesizing here, and we went to then just to very quickly make this is the lithographic based system. Why I am saying always like one infrastructure in all country, because someone has this kind of the facility, but someone has the no facility. If everyone has the same facility, then the players can be choose very easy from the India. But unfortunate from the ISC or few places, only these kind of the facility, and players are sitting many places, but they cannot open their mouth. But I am saying like to government to even the convince from my voice, one country required one infrastructure. It may be they can reduce the all PhD institutions, and they can only 10 or 20 they can run, but the infrastructure should be same. And we made the device, and ultimately we get the quantum Hall resistance. Because if you you can say in Hindi, jiddi, if you very motivated, then you can get your goal. So ultimately we get the quantum Hall resistance there. Similarly, I will just to very quickly within few seconds I will discuss about, we also developed the twisted bi-layer graphene. It's a very important area because people very clever. First we are trying to make the bi-layer, but we didn't get the advantage because spectroscopically double transition is occur because of the bi-layer. So what is the best gain for the making the 2 electrons parallelly? Then you can make the 2 layers, and logically you can arrange it. So when you could change the temperature by the 2 bi-layer, it can make the twisting. If twist angle is like 1.1 degree, like the magic angle, so you can make the more fringes, so you can easy to get the Cooper pair like the superconductor. So many applications you can use like this kind of the graphene structure. So after our report, if you see here, even the Raman measurement is very important to see these several data points to record. Otherwise, the measurement can be wrong. So we make like the 100 points for our the single layer graphene, and ultimately you can see the quality of the graphene. And also when people reported for the twisted bi-layer, they quoted our results also, the temperature dependent twisted bi-layer. So we done many things for the graphene. Very quickly I will just to finish the MOS2. Similarly we make the device for the MOS2 the growth, or MOSC2 or WSC2, because the limited time, so I will just to go to our terahertz results only. So there is different shape you can able to grow, depends upon the ratio of the molybdenum and sulfur. So depends upon the mass, depends of the rate, temperature and everything. So you can able to make different kind of the structure. Even we had also made our lab the heterostructure like the NBSC2 or like WSC2, like the thin diode structure. And if you see the recent our work, we also, I will just very quickly to go there because already chairperson is saying about the alarm. So we also making the WSC2. And if you see here, like we recently reported for the electronic triggering of the single layer graphene. So we are trying to delocalize pi electron to trigger by the applied voltage and change the frequency of the terahertz. So first time we are reported for the tunable terahertz frequency using these kind of the single layer graphene. So this paper recently published in the last month. So another kind of the area what I am talking about, that the MOS2. So you can see here this result is very important. I will discuss here. So if you see here the bulk and the difference between the monolayer, if you see the absorption is very high in case of the bulk, but if you see in the monolayer, it's like very small shift and change in intensity almost like negligible. So that's why we are looking for the MOS2 and the graphene heterostructure to make the tunable terahertz with the optimum best efficiency for the terahertz applications. And this is some conclusion for my work. So I'm just to summarize or given the glimpse of the work, not the actual the detail of the work. And recently one work I would like to introduce here. Recently one of our product, the new, as you know, the NPL developed 1954 election ink many years ago. Till date there is no replacement. So recently we developed another election ink for the India, and this is invisible on the finger, or once you are putting the particular device sources, then it will glow. And this experimental already tested on the CSIR headquarters, and more than 400 samples already done successfully, and hope very soon you will see in the elections. Thank you very much. And this is thought of my life. So I will say to read. It's a 1 minute it will take, but it's very important for the students to make. So make yourself as an iron. No one can destroy you. So even people will understand and listen sound of your hard work, which make you may iron. So if you make yourself as a cotton, everybody will praise you, and you enjoy. They will enjoy, and change your life will be hell. So make yourself iron, not the cotton. Thank you.
The house is open for questions.
Pardon? Last 3 years we are working. So first we are tested on the animal, then we are tested on the human skin. So there is a protocol we fully followed. We have the collaboration with the NII. They have the experts for the biological testing.
I think in view of paucity of time, we will have no more questions. Let's move on to our next speaker. Yeah.
We can save time.
I now request invited speaker Professor Praveen P. Ingole from Department of Chemistry, IIT Delhi, to please join us on the dais.
Well, it's my pleasure to invite our second keynote speaker, Professor Kedar Singh from School of Physical Sciences, JNU. Professor Kedar Singh is currently working as Professor of Physics and Dean of School of Physical Sciences, JNU, New Delhi. He has done his PhD from University of Rajasthan in experimental condensed matter physics. His research interest includes experimental condensed matter physics, materials for energy applications, DMS quantum dots, peroxide quantum dots, core shell materials, geo-nanohybrids and composites, transition metal dichalcogenides, phase change materials. Very briefly, he has over 150 publications with a total citation count of 2633 and H index of 29. He has been awarded with Raman Fellow for postdoctoral studies in US under Indo-US 21st Century Knowledge Initiative Program 2013-14, availed at High Magnetic Field Laboratory, Florida, USA. He has a number of awards to his credit.
Okay,
and I would request the professor to please start his talk.
Okay, thank you.
Sir, we will limit the talk to 20 minutes.
Please let me know, then I will. Okay, thank you, Professor Mehta, for nice introduction. I am also thankful to organizer invite me here to for deliver a talk on this is the basically I will my talk is quantum dots. Most of this is the work done by Dr. Gupta, because he lot of things say on the quantum material. But just I am little bit specific here. If you see in this year, Nobel Prize going on, this is the discovery and development of this is the quantum dots. Just 3 persons. This is the Mowgli, and this is the Louis Verne, and this is the Alexei. This is the 3 persons. They get the Nobel Prize on this is the only this is synthesis, and this is the quantum dots. If you see this is the bark of this is the 3-1. This is the if you see this is the Louis. This is the synthesis. This is the quantum dots, colloid quantum dot. But the second one, if you see this is the this is the Alexander. He sees some effect on this is the quantum dot in some glassy materials. Then how it will work, how property will change. Then these are the some things are here, but I am not going here. But if you see for Mowgli, he did he takes some solvent. Then there's a hot injection method to prepare quantum dot. You can see it here. And if you see some crystal will grow here, then there's some injection, then hot injection, then this will get cool, then heat it again, then this is the formation of this is the quantum dots. Just yes, if you see here, this is the how we can explain quantum dot, how this is the density of state will come. This is the for 3D material. This is the for continuous state will come. For 2D, this is the later side. Then if you see for 1D material, it will come here. If you for quantum dots, this is the if you see this is the quantum dot, your discrete energy level will discrete thing will come here. Then here what will happen? Here optical property and other property entirely different as compared of the bulk material. This is known as the 0D. But this is the 0D in terms of this is the this is the dimension is the less than 10 nanometer. But really this is not 0 dimensional. But as compared to the bulk material, we can say this is the 0. If you see in the nanomaterial, that game of number of atoms. If you lose the number of atoms, then you will see for bulk material, this is the density of state. But if you go quantum dot, series of quantum dot, if you go for individual quantum dot, it is showing some. This is some individual thing. Molecules, same thing. You will go here, then atoms. So sometimes quantum dot is known as this is the artificial. This is the atoms, because this is assembling of the some atoms are here. But just this is the quantum dot, or just I want to quote here. Then the Nobel Prize Committee also said this is the colorful nanotechnology, because if you see here a lot of colors, you can see for this is the quantum dot. The quantum dot dissolve in the toluene here. CDSE quantum dot is for quantum dot to large quantum. You can see this is a different color is coming here due to change of this is the band gap here. So beauty of quantum dot, if you can change this is the size of quantum dot through controlling of the reaction time and reaction temperature. So that's why you can see this is some example of quantum dots. ZNS, CDSE, this is the examples are here. Just pure quantum dot, the diffused very easily. So that's why then we need some doping. For a second thing, they also change the this is the properties. That if you dope, this is the some transit metals, ions, and the inter defects create here. They alter their optical property, magnetic and electronic property. So then we can make it as a functional material, or then it can be used for different applications. And here for quantum dot, you need some quantum confinement. Quantum confinement happen here. This is the widening of the band gap, you can see where electron and hole confined in a particular region. This is the two types, big quantum confinement, holes and electron confined in a very small region. Here you can see this is the, this is the Bohr, this is the radius is very, very small as compared to, this is the dot. Strong quantum confinement is the Bohr radius and, this is the radius of quantum dot is same. Then you can see here holes and electron confined in a very good region. Motion of electron hole are confined individually. So this is important here. And now question is here, how do you know this is the quantum dot or not? By experimentally, so this is the very simple experiment, absorption spectra. If you are able to get this peak, this is known exciton peak. So then you can say this is the quantum dot. Then this peak is also very with, this is the change of size of quantum dot. You can see it here. This is the CDSE quantum dot. This is going to change here. And also absorption spectra, you can see here. This is the small quantum dot to large quantum dot. Absorption spectra is also systematically going to change here. If you put quantum dots in UV spectra, UV lamp, then UV quantum dot will glow here. And this is the why we are considered quantum dot below 10 nanometer. So this is the, if you see the more radius, most of this is the element is below 10 nanometer. And second, if you see this is the graph here, if you see band gap is very up to, for most of material up to 10 nanometer, most of optical property and this property will change only this region. So that's why we consider quantum dot below 10 nanometer. This is some synthesis of the quantum. There are two techniques here. This is the bottom to up approach. Then you can see this is the colloidal synthesis. Here what we will do, we will assemble atom to atom. Then this we can control through reaction temperature and reaction time. Other is the top to down. Here what we will try to reduce the number of atoms. Number of atoms will less and less. Then it will show you some quantum confinement. Here, but this technique is costly also. Also, we cannot, control the size of quantum dots. So this is the things are here. Yes, for the top to down approach. Just I want to show you why. This is some lot of nowadays. There is a lot of application of quantum dot. You can see this is the biomedical, sprontronics. A lot of application you can see nowadays. Or lot of field is going to open here of quantum dots. But this is the one application, the sprontronic application. This is the application mostly for dilute magnetic semi-quantum dots. Here, what we do here, if you see, this is the, we can control spin polarized current here. Advantage, spin interaction is less as compared to the, these things are here. But just I want to show you my work. This is the, when I was in US, and this is the work. Chromium doped, this is the ZNSE quantum dot. Here we find here, this is some, this is the, if ZnCr2Se4 is inclusion in ZnSE. But how we can synthesis? This is some, this is a lyothermal method. Here we take, Zn10 cluster, and this is the source of chromium with the chromium chloride. Then we make it the reaction conduct in nitrogen environment up to 220 degrees centigrade. Then this is the some purification we did it. We take, this is the absorption spectra. You can see this the peak is coming. This peak is coming here systematically. If you enlarge this part, then you will get some hump also here. It is showing chromium 3 signature is here. Then we take, this is the X-ray fluorescence. Then this is the, we take, this is the ratio. Ratio is not going to change. Then we can say this is the chromium is doped inside of zinc. This is the XRD. You can see this is, it is showing cubic structure. This is the dope. Then this is the TEM images. Bunch of this is the quantum dot is here. Then majority of quantum dot is this is the 2.8 nanometer. This is the EPR. You can say for room temperature to this is the low temperature up to 5K. Here what will happen? This peak is the pressure peak is widening here due to the chromium interaction and antiferromagnetic interaction coming here. And this is the EPR at different frequency and fixed temperature is the 10K. Then you can see here. Then this is the, then we are able to calculate G factor. If you see G factor is coming, this is the 1.9808. This is the, if you see for literature, this is coming chromium 3, again, this is the confirmation. Then we take, this is the magnetic measurement through this is the squid. Then you can say this is the temperature. Then we take 1 upon here, this is the temperature. Then this is the, if you see this is the field, then we take it. It is showing some, some interaction here. Then this is the some dimagnetic thing are coming here. Other work is the on the, this is the same for the quantum iron doped Z-massive quantum dot. Here we prepare 1%, 5 and 10%. This is the, iron doped Z-massive quantum dot. Here you can see this is the dot size is very, very small. This is the 1.8 nanometer. And here this is the my work where is the, if you see this is the EPR at room temperature. Here we get iron 3 is doped in, this is the, in this Z-massive quantum dot. But I want to show you here, this is the DC squid. You can say this is the zero field cool and field cool. You can clearly you can see it here. Then if you, this is known blocking temperature. Then blocking temperature is increased when we increase the doping of the iron in Z-massive quantum dot. And this is the AC squid. Then we take chi double dash things here. Then if you can see this some this is the at the 25K. This is the some some transition is coming here. Then you can see for higher concentration. By the help of this is some Maydos criteria. By the help of Maydos criteria, we can say this is the spin glass or super paramagnetic material. If you see for we calculate, this is the Maydos criteria. Then for different concentration of iron, if you see for this is the for 1%, it is showing super paramagnetic material, because this, if you go for higher concentration, this is the 5 and 10, it is showing some spin glass behavior in Z-massive quantum dot. So this is the finding here. Other is a core cell quantum dot. When you will take two quantum dot, one can be core, other can be cell. So then what will happen here? The property will be changed. And second step, this is the stability will also increase of the quantum dot. So just I want to show you some, this is the, we prepare CDSE B205 core cell quantum dot for different concentration. Then here one is the for thick and thin, then we give the some name here. Then what, then you can see this thing coming here. Just I want to show you some, this is the absorption spectra. Then you can see this is the absorption spectra. CD is the shift, huge shift, you can say this is coming here. So this can be some code. And emission property, there is no more change in emission property. You can see it here after, sailing over CDSE quantum dot. Then we take, the femtosecond. Then you can see, then we calculate quantum yield. Quantum yield also increase when we, then this is the CDSE, then this is the sailing of, B205, this is the quantum dot. And just I want to show you, this is the XRD showing some, this is the hexagon, this is the rubber spectrum is okay. Just I want to show you. This is the TAM image, you can see for pure CDSE, then this is the CDSE B205, this is the for 3 nanometer, this is a 4.5, then this is the for 6 nanometer is coming here. Just I want to show you some application. This is the ultra fast spectroscopy we did in NPL. Then you can say for CDSE B205, then this thing. Then by the help of this, this is the direct transition for CDSE. This is the direct as indirect transition for CDSE B205. Then here what will happen? Here electron cooling rate degrees. If electron cooling rate degrees, then such type material can be useful for photovoltaic application. So this is the conclusion here. And other thing also some our this is the my colleague also did some biocompatibility, because this is a CDSE, the toxic this is the material, but it's a B205, this is the cell over here. Then you can say this material is a more biocompatible as compared of the CDSE. Then you can see here this is some different concentration here. There is the coming. And other application, other material, zinc, gallium, sulfur quantum dot. This is the ternary quantum dot. This is a very, we take it here for very simple method. Then we get it. Then what we do is we change zinc and gallium ratio here, then this is coming here. Then we take, this is the absorption spectra, it is showing some, this is some quantum dot thing. Then we calculate band gap, it's coming about 3.15 electron volt. Then this is the, you can say, PL spectra, it is showing different peak are coming are here. Then if different peak is coming, then what will happen, this is showing some different state, if you see it here, in here. So then size is about 3 nanometer. Then we calculate, some, this is the femtosecond thing. Then the conclusion here, if you see, then if you see for zinc, selenium, band gap at 3.494 electron volt, this is the stable material. If you go for gallium sulfide, this is the band gap about 2.5, but if you take gallium, zinc, gallium and sulfur, this is the band gap is about 3.1 nanometer. This is showing some different state also. So this is, again, this is the material suitable for, for photovoltaic applications. Why other, this is the new, we prepare some, peroxide quantum dots. These are some new things here. Then what we do, we synthesis by some oxalic acid, you can see it here, then put it something, this is some method. Then if you see, then we glow it, it is coming, some, this is the things are coming here. Just I want to show you, this is the TAM images, you can see it is showing very good, this is the, TAM image is showing, this is the hexagonal things are coming here. This is the absorption spectra, you are getting peak. And if you see this, the PL spectra, it is showing very sharp peak, about 500, this is the wavelength. So this is the green things coming here. Then this is a femtosecond. And X-side is also showing some, hexagonal things are here. This is the some femtosecond, we did it for different, this is the, energy, we take it here. Then we are calculating, and this, just I want to show you my other work here. This is a recently published paper really. This is the, if you see, this is the magnetic property CSPV-BR3 peroxide quantum. If you see, this is the quantum dot, basically this is the dimagnetic material, but due to some defects, they're showing some magnetic properties, so we study it here. Here, what with this is happened due to, some bromium, this is the showing, and this is the some different oxygen state of, this is the PV1 plus 1, PV2 and PV3, a lot of things in, then we get some, different, this is the magnetic transition in this material. How we can understand? This is the magnetic property, temperature versus, the magnetization. You can see this is the zero field cool and field cool. Here you will get some transition are coming here. This is the 35, 56. Then if you enlarge this thing, then you will get, these things are coming here. Then you can see different transitions are coming here. And also we take it different field. It is showing some different property. Just this is okay. Sorry. This is also arrow. Pilot is also saying the same story. There are a lot of things are changing here. Finally, what we calculate some, this is the parameters by some theoretical approach and some experimental, this is the things. Then this is the some, this is the some, if you see saturation magnetization, you can see this is going to change more and more this region. Then also we calculate the number of spins. Number of spin, you can see for beginning, this is a huge change, after there is no change. But if you go from 100, then get some change. And this is some energy also we calculate for this energy, it's also coming here. So if you see, then what we get, this is some Nuttall-Ward story, latest distortion in crystal structure of BR host CSPV-BR3. This is the things are, you can see this structure is here. Then this is some angle and this is change. Then this is the for PV. This is the oxidation state is also going to change here. This is some dimagnetic property. Then PV, then BR -1. This is a PV1 paramagnetic properties. Then this thing. Then again it is showing the ferromagnetic property. So this is the structure of the here. I have time for 5 minutes. 2 minutes. 2. Okay. Other, this is some EMI shielding material. This is also very good nowadays application. If you some electronic devices, mobile, there are some EMI interface things are there. So a lot of disturbance occur here, then how you can shield this, then you need some EMI shielding material. For this material, you need some lightweight material, stable material, and it should be also not toxic. So then this is some theory about this. Then this is some material. Then how this is the absorption, then emission, then things. Then how we can this is the vector network analyzer. You can see we put material here, then we take it here. Just I want to show you some result here. This is again this is the paper. This is the work is published ACS Applied Matrix and Interface. Here we prepare CNT MOS2 RGO nano hybrids. You can see this is the very simple method. We take it. This work is done by Jagdish Prasad. Now he is doing postdoc in Korea, and my other team also. And here you can see this is we take this something. Then this is and finally we get this. Then we take this is the XRD. This is the so here just I want to show this is the 10 images. For this is you can see this image for RGO, and this is MOS2. There are some MOS2 RGO. This is you can see this some nanotube is also coming somewhere here. Some structure is coming here. Then we take this is the 10 images. These are 10 images. You can see this is coming here for RGO and this thing. Then you can see some nanotubes. Things are you can see rupturing here. You can see. Just this is the EMI shielding due to this is the reflection. Then you can say for MOS2 this is 4 and this is going to down. This is not stable here. If you go for MOS2 RGO, this is not so stable, but this is due to the reflection. But if you go for absorption, then you can say this is stable. And this is not so stable, and if you go for higher consistent, but if you take the both, then you can see this is a more stable. Then this is the 40 decimals. So this is the something then we are able to get same thing. If you consider here so then this is the huge. Why it is happening? So this is the some systematic. Then how we can understand. Here this is the RGO is here, then CNT, then MOS2. So here is the migration of electron, hopping of the electron, dipole, a lot of things are going to happen. So that's why we are able to increase, this is the EMI shielding property here. So this is my student did this work. This is my former student, and Jagdish did this work, and my postdoc, and this is the collaborator, Professor Naresh Dalal, Jeffrey Strauss. Pratima Solanki did, this is the, if you see this work, biocompatibility, and Jasri for this the iron doped CSB. Then thank you very much for listening to my talk. Sorry, I take 2 minutes more. If there is any question, if there are any questions, we have time. We can take a couple of questions. If you see, lyothermal means we are heating, then also same time we are cooling through nitrogen. So this is the lyothermal thing are coming here. So then you will get very good crystals there. So this is the application. And then also you can save some oxide things, because this is the nitrogen environment. So this is the application of lyothermal.
Sir, I have a question.
Yes.
Yeah, please go on.
Yes, if you see, this is the interaction things. If you see, then this is the deep. We need to study really for this one. Which type interaction is coming here? But this is very good question. We need to some theory. We need to do. Then we can get some interaction things really. I am searching some theory person. Then how we can explain this thing. We need a lot of things. A lot of interaction can be there. Yes,
I can reply. What you asking, because she is asking very important question, because in RGO, basically oxygen and the terminal bonds and the MS to the sulfur. So totally both are, alienation kind of the situation, then how it can be interact. So basically it's a intermixing kind of the composite. It's not kind of the virtual interaction between the coordination, any kind of the, you can say covalent or like van der Waal or anything. It's just like to mixing. Yes.
Thank you. Oh, okay, please. Okay. Yes.
Yeah, please.
Have there been instances of when they do IV measurement for fluorescence, there's some expressive effect is seen?
Yes, if you see, sorry?
Do you think it is related to the lead movement?
Yes. This is written by, this is the some, lead is showing some, this is the some different oxidation states, then bromine creates some, defects there. So that's why it is coming really. So.
I've seen in one, just curiosity coming to mind, like cadmium sulfide with lead doping like a long term, and I ended up getting some membrane certificate.
Yes.
That movement we actually gave the reason for that. Sort of injection.
Yes, it may be also possible.
I have a just small question.
Okay, yeah, because you have chemistry.
I'm a chemical engineer by education. So
Work-related chemistry, yeah.
Yeah. So I was just wondering, maybe I'm being naive, but how do these compare with the quantum dots from, coal or graphite, graphene quantum dots, carbon quantum dots?
Yes, if you see, this is
especially for biological applications.
Yes. Then because my interest is for the, if you see, this is the inorganic quantum dot, especially I am telling you. But if you see for the organic quantum dot, they are not so stable. So one thing, so that's my interest is not there. But these quantum dots are more stable as compared to the carbon, especially for graphene quantum dots. So
People are coming up with, devices of sensor using
yes.
the sensor.
It's a
Well,
very good area also, if you see.
Okay.
I'd like to add, because it's a very important question and proper answer is very important. Because if you see the perovskite quantum dots and the other quantum dots, quantum field is very, very high, about to 1. If you talk about the carbon dots, the quantum field is less than 9%, 10%, even sometimes less than 5%. So if you want to biological imaging, you need to cellular imaging very strong fluorescence. Otherwise, autofluorescence will be going to affect the background. So, you cannot able to see the difference between the cell and the tagging. So then that's why the high quantum field materials are required. So what
Yes, definitely you need some.
that is the major advantage of the perovskite on the others. Yeah. The most important part is to shown the first slide to the Bondi that work. They struggle last 23 years. I'm surprised to what is the happen in the. When they collaborate with the Samsung in the Korea and they make this table. Can you, if anybody has in this hall like Samir Sapra, our friend is there. So I'd like to know what is the happen in the industry, how they make this table, the Bondi, that quantum dot to make a stable instead of the unstability. If you know, then you can otherwise.
If you see for industry also coming this area, now if you see lot of, this the main thing is the synthesis, how you are going to synthesize quantum dot. Lot of people working in this area, then they are coming.
But once it is going to Samsung only, they are going to in the industry to.
No, industry is a different issue than
what
industry.
Is science? The stability.
Yeah, science. Then because stability is not only one issue here. Stability, you need some doping, some this is the core cell quantum dots, lot of structure change. Then it's going on here. Then after Nobel Prize, people are working more and more. Then how we can find the things there? So they are going on there.
Well,
Yes.
let's thank Professor Kedar Singh.
Okay, thank you again for a lot of discussion really. Okay. Thank you.
Thank you very much. So our next invited speaker is Professor Praveen P. Ingol, Department of Chemistry, IIT Delhi. I'll read out just a brief introduction to Professor. Professor Praveen has done his PhD from University of Pune and has been a recipient of DAD Fellowship. He has done his postdoc from TU Dresden University of Germany. He has been working in Department of Chemistry in IIT Delhi since 2013. His research interest includes fabricating nanoelectrocatalysts for the electrochemical conversion of organic pollutants such as CO2 into fuels and or other useful chemical feedstock. Secondly, his interest is in electrochemical and spectroelectrochemical studies on the advanced function materials in order to characterize and tune their electronic band structure. And thirdly, developing photoelectrocatalysts based on semiconductor quantum dots for photovoltaic solar cell applications. His group also works on studying the mechanistic aspects and electrode kinetics of the organic reactions, especially electrocatalytic reactions in ionic liquids. And lastly, he has around 150 publications with a total citation count of 2254 and an H index of 26.
Thank you.
Professor, please.
Thank you for the nice introduction, as well as the organizer for this opportunity to present some of our work. Well, I know this is a difficult task to be at the tail ender and to finish the event, the day's event. And I'm going to say sorry to the cameraman because I'll be moving here and there, so it will be trouble for you. Sorry for that. So today I'm going to present some of our research work that we have been doing in our lab at IIT Delhi. And mostly as a trained electrochemist, I look at the electrocatalytic properties of some of the materials that are important for some of the reactions, particularly for the sustainable production of the fuels and the chemicals. Okay. So I'm Praveen, I'm working in IIT Delhi Department of Chemistry as a professor, chair professor for Bhandari and Sangla. Its mandate is to work on the green hydrogen and the CO2 capture and conversion. That is what I am being paid for. I think I have to go here. Yeah? So this is not going to work. Okay, so today I'm going to present one. I'm audible there, back? Okay. So what I'm going to tell you, one of the physical chemistry aspect. If you heard about the Sabatier's principle, the Sabatier principle tells us that there should be an optimum adsorption of the reactants on the surface or any catalytic process. If you take the photocatalysis process, chemical catalysis process, thermocatalytic process, or in the electrocatalytic process. Now, these Sabatier's principles, how is helpful for us to tune the electrocatalytic properties? I'm going to present in these two examples. One of the examples is the carbon dioxide conversion to the carbon monoxide. This is one example. And another example, I'm going to present you the bifunctional oxygen electrocatalytic activity. Bifunctional, what I mean is the oxygen reduction reaction and the oxygen evolution reaction. These are two functional ways. So what we do much on this side, if you look at the photosynthesis process, you can compare this with the natural photosynthesis. And I call it artificial photosynthesis. On one side of the electrochemical cell, what we do is we convert the water molecule into the oxygen, and the protons are generated. The protons migrate to the other side of the electrode cell, the electrochemical cell, and you have the carbon dioxide in the next cell. Now this second half cell, the carbon dioxide is reduced on the cathode surface. It can also combine the protons and it can make the fuels. So our idea is to make the hydrocarbons from the carbon dioxide. Now whenever you do any electrocatalytic process, the important steps that we can see is that the reactant is here, then it has to migrate or it has to move to the surface, maybe by different modes of mass transfer. It can be migration, or it can be diffusion, or it can be convection. Once it reaches to the surface, then it can undergo the electrochemical reactions or photochemical reactions. But the important point is the reactant should go on the surface and should stick there. Unless the reactant goes there, and this has optimum binding energy, you are not going to get the catalysis. Why? Because if it is not adsorbing on the surface, there is no electron transfer process or no reaction is taking place. If it is going there and it is sticking very strongly, if it is binding very strongly, then the product will not come out from the surface. And in a way, it will poison the surface. We know this as the catalytic poisoning in the chemical engineering, right? So what our quest is that can we tune this electrochemical interface? Now, when we say electrochemical interface, it includes both. It includes the electrocatalyst as well as the solution side. So we work on both the catalyst as well as the electrolytes. But today I'm going to present some of the recent research work that is mostly focused on the catalyst. And this is the Sabatier principle that I was talking about, who was awarded the Nobel Prize in Chemistry in 1912 for this discovery. So this is the optimum that we are targeting for. So this optimum, what it does, it is the bond strength, is for the adsorption, right? The reaction rate is very high at the optimum. It is Low, if it is the adsorption is weaker, because then you don't have the sufficient time for the catalysis to take place. And if it is very strong, then the catalytic surface gets poisoned by the intermediates or the products. Okay, so that is what we are doing, we are trying to do. Besides that, we are trying to address another issue. Like if you look at the state-of-the-art catalysts, they are mostly the noble metal-based catalysts. And we are trying to avoid the noble metal catalysts because so that we can make these processes feasible at the industrial level. Now, the first example I'll show you how this Sabatier principle is helping us to tune the electrocatalytic activity. If you look at the CO2 reduction, again, if I'm shown here the mechanism, the first step, the carbon dioxide is coming on the surface and getting adsorbed, right? And this electron transfer is taking place. Then subsequent electron transfer processes are there where it can make different products. I'm not going to the details of the different products. I want you to focus on this panel. Okay, what is happening over there? Of course, when I say the electrocatalytic reduction of the CO2, this is a top job. There are different parameters which we need to take into the considerations. Besides conversion, now we recently started on the carbon capture. This is an integrated process, right? The carbon capture and the conversion by using the different ionic liquids and the diuretic solvents. I'm not going to that part. I'll come to this first part. Again, I want you to focus on this step. Now, we took this example, the strontium titanate. The strontium titanate, this has certain inherent oxygen vacancies. And these oxygen vacancies are known as a good adsorbent for the CO2 molecules. So whenever the CO2 molecules is coming on the surface, these oxygen vacancies provide the surface sites for the adsorption. Now our aim was, can we increase these surface sites or can we increase the oxygen vacancies? We thought of let's dope it with some of the transition metal elements. We took an example of the chromium, right? You can see this, here is the chromium is coming, okay, and it is replacing the titanium. When it is replacing the titanium, it is doing two things. One, what it's doing is it's creating more oxygen vacancies, what we need for the more adsorption. Second, it is also changing the charge dynamics. If you look at the Bader charges, I'm going to show it. It changes the dynamics at the electronic environment of the oxygen vacancies which are already present there. Okay, this is the two things that we are going to address. So for that we did prepared chromium doped H2O samples, strontium titanate samples for different concentrations, and what we found is that this, as we change the concentration, there is a peak shift which is more clearer in this image, okay? And slight shift, it's suggesting that there is the doping of the chromium. If we increase the dopant concentration, let's say 15%, then you will see that additional peaks are also appearing, which is suggesting that in addition to the chromium doped H2O, you have formation of some other phases, okay, which is not required because we wanted to study what is the effect of the chromium doped. And so if you look at the size distribution curves, you will notice that there is hardly any change in the size. So size is not playing a role, that is we confirm. Second, the phase separation is not playing a role. So whatever the effect is there, it's because of the doping. Oxygen vacancies we quantified using the XPS. You can see this is for the without doping, this is for the doping. The oxygen vacancies are increasing. We have quantified these oxygen vacancies using a very simple technique. This is thermogravimetric analysis. So you can see that weight loss is corresponding to the coordinated waters, which is there on the oxygen vacancies. Higher the weight loss of the coordinated water, higher is the number of oxygen vacancies. Now, if you come to the electrochemical setup, what we have is this is the electrochemical cell made up of the Teflon. It's a two-chambered cell. One side you have the water and the anode. The other side you have the carbon dioxide and the cathode, which is separated by the proton exchange membrane, which is called the Nafion membrane. When you record the cyclic linear shift voltammetric curves, these are the linear shift voltammetric curves. The dotted lines are the argon. The bold lines are for the carbon dioxide. You see there is a change in the current. There is increase in the current when we purge the carbon dioxide, right? Which means that the electrode is sensing something. So it is generating, what it's generating is actually it's converting carbon dioxide into something, okay? And we are not sure what is that something, okay? For that, what we need to do is we collect all the gases coming from this, and then we characterize with the gas chromatography. And the gas chromatography tells us that there is a formation of majorly the carbon monoxide. And this is the chart for the Faraday efficiencies for different dopant concentrations. We found that H2O5 gives the best Faraday efficiency, means this is the best catalyst among the different dopant concentrations. Also, we checked at different potentials, if for the H2O5, what is the nature. Then to check the stability or the recyclability of the catalyst, we have done these measurements several times. For example, here I have shown the data for the 12 times, right? So again, we have a very good stability of the catalyst. It can be reutilized several times. Now, coming to the post-mortem analysis, when the electrolysis is done, we take out the catalyst from the surface of the electrode, and then we characterize this. This is the XRD before and the after. This is the FTIR, and this is the XPS. Cutting the long story to the short, what we observed is the following. We observed there is an additional peak in the FTIR as well as the XPS spectrum. This is before the catalysis, this is after the catalysis for the strontium. What we found is that the strontium is now converted into the strontium hydroxide. Okay, and then which is also confirmed with this, and this is also confirming that there is no much change in the characteristics of the material. So it's a H2O is staying there as such, only some of the hydroxides are coming on the surface, and which is mostly binding to the strontium. So to understand this, what is exactly happening and why there is an increase in the yield of the carbon monoxide, we shifted to the DFT theory in collaboration with the Professor Dibyajyoti Ghosh in chemistry department of IIT Delhi. What you notice that, I'll show you this first. This is the H2O. The carbon dioxide is coming on the surface. As soon as the carbon dioxide is coming on the surface, this is the corresponding reaction. It is getting adsorbed on the surface. It's also abstract the proton from the water, and it makes the COOH on the surface. This is very facile process because you can see this is the exothermic process. Now, once this is done, now the next step is actually this breaking of the COOH into the CO, which is adsorbed on the surface, and the water molecule. So CO is formed. This is also a feasible one, but next, when we go to the desorption step, this OH, which is being formed there, this OH has to dissolve as the water molecule. Now, if I compare, this was for the strontium titanate. Now, if I compare, now the reds, if you look at the red points over there, this is for the chromium doped strontium titanate. What you can notice is that the first step is almost similar because of the number of oxygen vacancies is not altered that much. There was little increase in the oxygen vacancies. Importantly and interestingly, what we found is that this step, the desorption of the OH molecule, now this is much favorable as compared to the undoped sample. And this is because of the chromium which is coming into the picture. The final step is also similar, only this product desorption step, which is actually now more favored on the surface. And why this is favored? If you look at the Badder charges, chromium is plus 0.51 as compared to the titanium, which is there in the pristine H2O molecule, which is 1.25. So lesser electropositive character of the chromium is actually helping, or the Badder charges surrounding the chromium, lesser Badder charges is helping this desorption of the OH from the surface. So even we can target the product desorption step, and we can enhance the catalytic activity. That was the bottom line of this work. Next, maybe I'll 5 or 6 minutes, I'll try to present another example for the electrocatalysis, and particularly we have taken this example, electrocatalytic oxygen bifunctional activities, where you can see this is the metal layer batteries, and these are the important reactions, oxygen reduction reaction and oxygen evolution reactions. Now we can look at this. This is similar to the Sabatier principle. This is the Sabatier optimum where. And the optimum, what we can see is the platinum, palladium, these are the high cost element, metallic materials that are most active. On the left side, you have the very less active. On the right side, these are also very less active. Similar curve is there for the oxygen evolution reactions. Now we thought of to come up with the materials. Now one important point what you can notice is here, oxygen reduction reaction, platinum is the most active, but if you go to the oxygen evolution reaction, iridium dioxide or ruthenium dioxide is the most active. And platinum is not a good catalyst for the oxygen evolution reaction. So that is the catch. The material is not showing the bifunctional, the state of the art materials, they are not showing bifunctional activity, means a single material is not useful for the two applications. Now to use these materials which are low cost, we wanted to understand their physical properties. And to understand that, what we thought of we can change, we took the example of the Prussian blue analogs. Prussian blue analogs having the Fe and the Cn linkages. It's a metal organic frameworks. Now, if you look at this, the paper by the Noskov in the Nature, what they tried to present is why gold is noblest of all the metals. They compared the theoretically nickel, copper, platinum, and the gold. And what they found is that the density of states near the Fermi level is an important parameter. And this is, downside is the D band. So D band structure, if you look at the D band structure, and particularly the D band center, the D band center plays an important role. As the D band center is moving, the number of vacant orbitals above the Fermi level are changing. Higher the number of vacant orbitals, stronger is the bonding of the adsorbate on the surface. Okay? So what you need is the optimum number of vacant orbitals above the Fermi level. And that is what we try to do for this application. For example, we took these Prussian blue analogs, and well, due to lack of time, I'm going to much of the details, but what exactly we have done, I'll go to there. So we played the chemistry, simple chemistry, inorganic chemistry, and what we did is we tuned the centers. One, you can see there is two different type of centers. This is the cobalt, for example, carbon, nitrogen, another metal, or the iron, carbon, nitrogen, another metal. You can change these metals centers, or you can fix this metal center and change cobalt to the iron. This is what we have done. So we call it the carbon coordinated one, and the other one we call it as the nitrogen coordinated one. For the nitrogen coordinated, we change the cobalt, nickel, copper, and the iron. And for this, we could change only the iron and the cobalt. And we checked its electrocatalytic activity. So synthesis, I'm not going to the details. We characterize these materials thoroughly and using different techniques, including the Raman and the microscopy. Coming to the electrocatalytic measurements. These are the oxygen evolution reactions. These are the oxygen reduction reactions. What you can notice is that among these catalysts, this Fe is a good catalyst, COFE, PBA is a good catalyst for the oxygen reduction reaction as well as oxygen evolution reaction. And these are just the number to show you, to compare this. Similar trend we observed for if I change the cobalt, okay, for the similar thing. What we observed is the similar trends where now cobalt PBA shows the highest activity in both oxygen reduction and oxygen evolution reaction. Now, having said that, now what is the reason why these materials are showing? Well, by the way, this is the trend. What is happening? This is happening. The cobalt Fe PBA is showing the highest activity. Fe PBA is showing very low activity. Copper Fe PBA is also showing the low activity. Okay. Now, to correlate that, what we did is we measured the valence band XP spectra. Okay, valence band XP spectra gives you the measurement of the D band structure. Now you can look at the break that we have calculated the average energy density of states. What you can see that this D band center is actually moving, and the change in the D band center you can correlate directly with the activity. For example, if you can see here till certain point, for example, the cobalt FeA is giving the highest activity, and where you can see here in this D band structure, they are lying over somewhere here. Okay. On the left hand side, you have very less adsorption. So left hand side is limited by the weaker adsorption. On the right hand side, you have the stronger adsorption of the reactants on the surface. So these are again similar results we obtained for the carbon coordinated metal centers. Again, we can correlate with this with the D band structure that we calculated from or derived from the. Okay, so this is what I have presented. I have tried to show you how the metal centers, which are coordinated with the nitrogen and the carbon, can tune the electrocatalytic activity. Overall, I have tried to show you is this, the adsorption of the reactants on the catalyst surface and the desorption of the product from the catalyst surface can be tuned by changing the electronic environment of the catalyst, and which can be used for the electrocatalysis. Finally, I would like to acknowledge my PhD students who have done this work, as well as some of my collaborator. Andras Safi is sitting here, Samir is sitting here. Also, I collaborate a lot with Seema Garg from the Amity University, and I thank all the funding agencies, and I thank you being here till the end and listening to me. Thank you.
Thank you very much. Anybody has any question, please go ahead.
आपने जो थ्योरेटिकल कैलकुलेशन दिखाया है उसमें प्लेटो स्टेबल प्लेटो जो एक्सपेरिमेंटल यू शोन द डेटा देयर इज नो प्लेटो सो आई लुक टू नो व्हाट इज द प्लेटो आई मीन because if you want to use in some application
which plateau
I mean CO desorption so if you see this is a theoretical calculation, right? So if you experimentally tested this mechanism, like this phenomena is basically site selective, right? So I'd like to experimental plateau, you have some data, I mean.
That is what I've shown, the XPS and the FTIR, where we.
But how we can quantify by those, I mean.
What quantify?
I mean, that plateau, how we can justify with the XPS?
Which plateau?
You are dissolving, right?
Of course, these are the energies, right? These are the energies
but
you
how
can calculate
it can
only
be,
by the DFT. You cannot calculate experimentally.
But suppose you use in some application, then obviously, I mean, the desorption in convert into some kinetics, right? I mean, how you will, this is okay what you are doing, but I'd like to know about, like you can use in some application.
This is the application. CO2 conversion to the carbon monoxide is the application.
But it's a directly, vigorously it's come out.
What come out?
I can just to
that is what
give
I
an
have shown,
example,
right?
like
See,
suppose,
what I have shown is.
What I want to know, I can just to explain, right? Suppose you are putting the sodium borohydride in water. I just to giving another example, not this example. Okay, so you can liberate the hydrogen vigorously. If you store the sodium, some hydrogen in some metal hydride, then you can dissolve the hydrogen. So there is two ways to, I mean, you can dissolve the, for application point of view. Like people now using for the CO even
so
dissolve.
You mean to say ki why this
yes,
is changing,
yes,
right?
Yes.
This is changing. That is what we observed in the quantification of the carbon monoxide. What we observed is that we change the doping concentration, we get the higher percentage.
Maximum site selective, that percentage is energy.
What we are saying is that this chromium dopant is actually tuning the electronic environment of the oxygen. Okay.
Sir, I have one small question.
Yes, please.
You had shown you had used catalyst for 11-12 times without any much drop in the.
Yeah. There is little decay in the activity, but yeah.
So, but since it's all, you also are claiming it's adsorption-based mechanism. Did you try to treat the catalyst after few runs in any way?
No. For taking this, we did not do anything.
Right. Yeah. That's okay.
Yeah.
But in, to make it better, can you treat the catalyst?
Now we are modifying the catalyst by different strategies. Of course, this is just the preliminary work, which is published, but we are also working on the other aspects. Yeah.
Thank you very much. Thank you very much, Professor.
Thank you.
Thank you all for the informative and interesting sessions. I'm sure it will be beneficial to all our listeners. Now, I request Professor Rajiv Mehta, sir, to felicitate Dr. B.K. Gupta, sir, with memento. Now I would request Professor Rajiv Mehta, sir, to felicitate Professor Kedar Singh, sir, with memento. I would request Professor Rajiv Mehta, sir, to felicitate Professor Praveen P. Ingole with memento. I would now request Professor Sunita Ratan ma'am to felicitate Professor Rajiv Mehta sir with memento. Thank you all for joining us. We have hereby concluded our today's technical session. I would request you to please join us tomorrow for another day of scientific learning and deliberations. Thank you all for joining us today.